For 4 billion years, Venus has been chemistry's graveyard, where sulfuric acid clouds at 93 atmospheres of pressure instantly destroy anything organic. Until November 3, 2025, when something survived. What arrived could rewrite our understanding of where life's building blocks can persist, transform how we search for habitability beyond Earth, and reveal that Venus hell itself might harbor chemistry we thought impossible. Japan's Akatsuki orbiter recorded the encounter in real time as Comet 3I Atlas, a 10-billion-year-old traveler from another star system, swept past Venus at 97 million kilometers, close enough to deliver its cargo directly into the acid clouds. But how can molecules from interstellar space survive battery acid in the sky? And what is Venus doing with them right now while you're listening to this? Tonight, we trace the journey of an ancient comet, carrying refined metals and organic precursors through the most hostile atmosphere in our solar system. We'll explore what shouldn't be possible according to chemistry textbooks, yet appears to be happening in Venus's upper atmosphere at this very moment. We'll examine the chemistry that arrived, the environment that received it, and the transformations unfolding in real time above a world we thought we understood. This isn't speculation about distant exoplanets. This is November 2025. The chemistry is measurable, active, and unprecedented in geological memory. The data exists recorded by spacecraft and telescopes. The analysis is underway. And over the next 2 hours, we'll explore what might be one of the most remarkable chemical experiments nature has conducted in our solar system in billions of years. Stay with me. The story begins not with Venus, but with understanding what Venus is and why what just happened there should be impossible. There's a reason ancient peoples watched Venus with such intensity, brighter than anything in the night sky except the moon. Venus dominates the pre-dawn and post-sunset hours. The Greeks called it Phosphorus in the morning, Hesperus in the evening, before realizing both were the same celestial body. The Romans named it for their goddess of beauty and love. They couldn't have chosen a more ironic name. Venus is Earth's near twin in size, separated by only 650 kilometers in diameter, nearly identical in mass and density, formed from the same primordial disk of gas and dust that birthed our world. For the first billion years of the solar system's history, Venus and Earth likely told similar stories. Both had atmospheres, both had water, both had volcanic activity shaping their surfaces. They were siblings walking parallel paths. Then something happened, something diverged, and Venus became what it is today. Standing on Venus's surface, if you could stand there without being simultaneously crushed, incinerated, and dissolved, you would experience conditions more extreme than most of Earth's most hostile environments. The atmospheric pressure reaches 92 times Earth's sea level pressure. That's equivalent to being 1 kilometer beneath Earth's oceans. The weight of the atmosphere pressing down on you from all sides. The temperature at the surface averages 460 degrees Celsius, hot enough to melt lead, hot enough that the rocks beneath your feet glow faintly in the darkness. This isn't the heat of proximity to the sun. Venus is farther from the sun than Mercury, yet hotter. This is greenhouse heating gone catastrophic. Carbon dioxide in the atmosphere trapping solar energy so efficiently that Venus became an oven. But the surface is not where our story takes place. Our story unfolds in the skies. Venus's atmosphere extends far above the hellish surface, stratified into layers defined by temperature, pressure, and chemical composition. And suspended within that atmosphere between 45 and 70 kilometers altitude float the clouds. Sulfuric acid clouds, not wispy water vapor like Earth's clouds, not frozen crystals like Mars's carbon dioxide ice clouds, concentrated sulfuric acid, the same chemical we use in car batteries, industrial etching, and chemistry labs. Droplets of it, billions upon billions of them suspended in the atmosphere, forming 3 distinct layers. The upper cloud layer between 60 and 70 kilometers altitude consists of relatively dilute acid 50 to 75% concentration mixed with water. At these altitudes, temperatures drop to comfortable levels, 0 degrees Celsius at the highest points, cold enough that water could condense as ice, cold enough that certain molecules can persist for meaningful timescales before being destroyed by other processes. Below that, the middle cloud layer 50 to 60 kilometers up thickens the acid to 75 to 90% concentration. This is where most of the visible atmospheric features form the Y-shaped patterns. Spacecraft cameras capture the vortices and waves that demonstrate Venus's atmospheric dynamics. Temperatures here range from -20 to -40 degrees Celsius. Deeper still, the lower cloud layer, 45 to 50 kilometers altitude, brings acid concentrations to their highest, 80 to 90%. This is the terminal zone. Most molecules that survived the upper layers finally break down here, either incorporated into droplets that begin precipitating downward or decomposed into components that rise back up through convection. These clouds don't behave like Earth's clouds. They don't rain onto the surface. The intense heat evaporates droplets before they reach the ground, releasing sulfuric acid back into gas, where it rises, condenses again, and perpetuates the cycle. This cycle has run for eons, a closed loop, a system in equilibrium with itself. And then there's the wind. Despite Venus rotating incredibly slowly, one Venusian day lasts 243 Earth days, the upper atmosphere races around the planet in just 4 days. Superrotation, scientists call it. Wind speeds at cloud level reach 100 meters per second. That's 360 kilometers per hour. Hurricane-force winds sustained permanently circling the entire planet. This superrotation, driven by complex interactions between solar heating and atmospheric dynamics, means anything entering Venus's atmosphere doesn't stay localized. Within hours, materials are carried hundreds or thousands of kilometers around the planet. Within days, they're distributed globally. For decades, scientists accepted a simple narrative about Venus: it's sterile. The combination of sulfuric acid, intense ultraviolet radiation, high temperatures, and crushing pressures creates conditions where nothing organic survives. Nothing complex persists. Chemistry arrives at Venus and dies. Venus became the poster child for uninhabitable, the cautionary tale of what happens when planetary evolution goes wrong. A reminder that Earth's habitability is precious, fragile, and not the cosmic default. Soviet engineers learned this firsthand. Between 1967 and 1984, the Soviet Venera program sent multiple landers to Venus's surface. The ones that survived the descent transmitted data for minutes or hours before succumbing. Venera 13 holds the record, 127 minutes before the electronics failed, cooked despite thermal shielding. The images showed a hellscape, flat rocky plains beneath murky orange sky, perpetual twilight. Venus's surface appeared dead in the violent sense of active hostility to anything complex. And above that surface, the acid clouds circled endlessly, recycling the same chemistry they'd been processing for billions of years. Until November 3rd, 2025. What happened that day, what's still happening now, weeks later, represents the first time in geological memory that Venus's closed chemical system received a significant external input, not from within Venus itself, not from the sun's radiation. From outside, from beyond our solar system entirely, materials arrived that Venus has never processed. Molecules that didn't originate in Venus's geology or its photochemical reactions. Chemistry carrying information from environments completely unlike anything Venus has experienced since its formation. And those materials didn't instantly die. They integrated. They began transforming. They started exploring chemical pathways Venus's atmosphere hasn't traveled in eons. To understand what that means, we need to meet the visitor. We need to understand what 3I Atlas is, where it came from, and what it was carrying when it swept past Venus at the closest approach an interstellar object has made to any planet in recorded history. The story of what happened at Venus begins with a journey that started before Earth existed. On July 1st, 2025, astronomers at the Atlas Survey Telescope in Chile noticed something unusual. A faint object magnitude 18, far too dim for backyard telescopes, requiring professional equipment to detect moving across the sky near the border of the constellations Serpens Cauda and Sagittarius. The object was designated ALN Polio 3Z, temporary identifier pending classification. Follow-up observations began immediately. Other telescopes swung toward the coordinates. Professional astronomers and dedicated amateurs started tracking. Within 24 hours, the trajectory calculations revealed something extraordinary. This wasn't an asteroid. It wasn't even a regular comet on an elliptical orbit. The mathematics told a clear story, hyperbolic trajectory, not bound to our sun, entering from interstellar space, sweeping through the inner solar system and departing back into the galactic void. On July 2nd, the International Astronomical Union's Minor Planet Center announced the discovery officially. The object received two designations, CE 2025 N1 Atlas, marking it as a non-periodic comet discovered by the Atlas system, and more significantly, 3I the Third, confirmed interstellar object. The first interstellar visitor we detected was Oumuamua, Hawaiian for scout, or STUS, messenger from the distant past. Discovered in October 2017, it sparked international fascination and debate. Its elongated shape, its peculiar acceleration as it left the inner solar system, and its non-cometary appearance led to extensive speculation, including fringe theories about artificial origin. The scientific consensus settled on a natural object, likely a nitrogen iceberg or highly elongated comet nucleus, but Oumuamua left as quickly as it arrived, and many questions remain unanswered. The second interstellar visitor, 2I Borisov, arrived in August 2019. This one was unambiguously a comet, active outgassing visible coma, and tail spectroscopic signatures matching solar system comets. Borisov behaved exactly as expected, providing a more conventional interstellar visitor to study. Now comes 3I Atlas, the third messenger. But unlike its predecessors, 3I Atlas is approaching planets closely, very closely. The trajectory calculations revealed something with extremely low probability. Random interstellar visitors entering the solar system follow paths determined by their incoming velocity vector and the sun's gravity. Most sail through the outer solar system or swing past at distances measured in astronomical units from any planet. The odds of approaching multiple inner planets closely are vanishingly small. Yet 3I Atlas's path was nearly perfectly aligned with the ecliptic plane, the plane in which planets orbit. Its trajectory would bring it within 0.19 astronomical units of Mars, 0.65 astronomical units of Venus, and later within 0.36 astronomical units of Jupiter. Statistical analysis suggests the probability of such close multiple encounters is less than 0.005%. Some researchers, notably Harvard astrophysicist Avi Loeb, have pointed out this improbable geometry while exploring whether 3I Atlas could represent artificial technology. These analyses remain firmly in the speculative category, but they've drawn attention to just how unusual this comet's trajectory is. Setting aside questions of intent or artificiality, the facts are remarkable enough. An object from interstellar space, likely older than our solar system, happened to pass 3 major planets at distances close enough for scientific observation and critically for material exchange. Where did 3I Atlas come from? Analysis of its trajectory traced backward suggests origin from either the Milky Way's thin disk or thick disk. These are distinct populations of stars with different ages and compositions. If 3I Atlas originated from the thick disk, the comet could be 7 to 10 billion years old, older than the Sun, older than Earth, older than any object in our solar system except pre-solar grains found in meteorites. This comet formed around a different star in a different stellar environment under conditions we can only infer. It was ejected somehow, perhaps by gravitational interactions with giant planets in its birth system, or by close encounters with other stars, or by its parent star's evolution. Once ejected, it traveled through the galaxy for billions of years. The interstellar medium is cold. Temperatures hover just a few degrees above absolute zero. 3I Atlas spent eons in this deep freeze, its surface ices pristine, its chemistry preserved in cryogenic storage, no solar radiation to sublimate its volatiles, no heat to drive reactions, just silent passage through the dark between stars until July 2025 when it fell toward our Sun. As 3I Atlas approached the inner solar system, solar heating began. For the first time in billions of years, warmth touched its surface. Ice sublimated directly from solid to gas. Materials locked away since the comet's formation began awakening. Observations from the Hubble Space Telescope. The James Webb Space Telescope and ground-based observatories revealed the comet's composition. Water ice, as expected, every comet contains water. Hydrogen cyanide detected through spectroscopic signatures. Carbon monoxide similarly identified. And then something unexpected. Nickel. Specifically refined nickel separated from iron. In normal cosmic chemistry, nickel and iron are inseparable companions. They form together in stellar nucleosynthesis. They exist together in meteorites. When comets outgas metals, they release both together. Finding nickel without corresponding iron is like finding water without hydrogen, a chemical impossibility under normal conditions. Yet spectroscopic analysis from multiple independent observatories confirmed it. 3I Atlas was ejecting nickel-bearing compounds, likely nickel tetracarbonyl, an industrial compound used in human metallurgy, without the expected iron signatures. This anomaly suggests the comet underwent processes resembling the Mond process, an industrial refining technique where nickel forms volatile carbonyl compounds that separate from non-volatile iron. How a natural object could undergo such processing remains debated. Possible explanations include extreme thermal cycling as the comet entered the inner solar system or unusual chemistry in its formation environment billions of years ago. Regardless of mechanism, the fact remains. 3I Atlas was carrying refined metals along with organic precursors. By October 2025, the comet was producing extraordinary amounts of material, water at rates exceeding 120 metric tons per hour. Hydrogen cyanide at roughly 80 grams per second, orders of magnitude higher than typical comets, carbon monoxide at similar rates, and nickel at several grams per second. On October 3rd, 3I Atlas passed Mars at 0.19 astronomical units, about 28 million kilometers, close enough that Mars's thin atmosphere intersected the comet's coma. Materials were captured and deposited onto the Martian surface, particularly in the southern highlands and polar regions. Multiple spacecraft, NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, China's Tianwen-1 observed the encounter, documenting the delivery. But Mars is cold, its atmosphere is thin. Materials arriving there settled onto the surface and froze, awaiting future investigation. The interesting chemistry at Mars would require human technology to unlock, scheduled for 2027 robotic missions designed to excavate and process Martian regolith. Venus would be different. On October 29th, Atlas reached perihelion, its closest point to the Sun. Distance 1.36 astronomical units just inside Mars's orbit. Solar heating peaked. Outgassing continued at intense rates. The comet's nucleus, estimated between half a kilometer and 5 kilometers in diameter, was fully active. 5 days later, still actively sublimating, still ejecting its ancient cargo into space. 3I or Atlas swept past Venus. The geometry was favorable. Venus wasn't positioned at a glancing angle like Mars had been. The encounter placed Venus closer to the densest part of the comet's outgassing stream. The coma, that tenuous envelope of sublimated gas and dust, extended millions of kilometers into space, and Venus's massive atmosphere, 93 times more massive than Earth's, presented a substantial capture cross-section. When the encounter occurred on November 3rd, materials from a 10-billion-year-old interstellar visitor met an atmosphere that hadn't changed significantly in billions of years. What happened next is what we're still trying to understand. But before we examine the chemistry delivered, we need to understand the exact circumstances of that delivery. We need to see the encounter itself. November 3rd, 2025, when an ancient messenger from the dark between stars kept an appointment with the evening star. The mathematics of orbital mechanics dictate precisely when and where encounters occur. There's no randomness, no chance. Given positions and velocities, trajectories unfold with clockwork precision. November 3rd, 2025. A 3I Atlas at 0.65 astronomical units from Venus, 97 million kilometers. To human intuition, that sounds distant. But in astronomical terms, it's intimate. The Moon orbits Earth at 0.026 astronomical units. Mars, at its closest to Earth, approaches within 0.5 astronomical units. Venus and 3I Atlas were separated by a distance that by planetary standards represents proximity. More critically, the comet's coma extended far beyond its tiny nucleus. Active outgassing creates an envelope of sublimated materials that can stretch for millions of kilometers. At 3I Atlas's distance from the Sun during the encounter, solar heating remained strong enough to sustain vigorous sublimation despite being past perihelion. Water continued flowing from the nucleus at approximately 120 to 130 metric tons per hour. That's the mass of a commercial airliner every 90 minutes, transformed from ice to vapor and ejected into space. Hydrogen cyanide production, which had increased exponentially throughout October, stabilized around 80 to 85 grams per second. Over the 4 to 6 hour encounter window, when Venus's gravity and atmospheric capture were most effective, that translates to roughly 1.2 to 1.8 kilograms of hydrogen cyanide delivered. Carbon monoxide continued at 60 to 70 grams per second, delivering approximately 900 grams to 1.7 kilograms. Nickel, refined and separated from iron through whatever process the comet had undergone, was being ejected at 3 to 4.5 grams per second. Over the encounter window, 50 to 110 grams of nickel arrived at Venus. These numbers might seem small. Kilograms of material delivered to a planet with a mass measured in trillions of kilograms. But chemistry doesn't care about absolute quantities. Chemistry cares about concentrations, reaction partners, and conditions. And the materials weren't distributed uniformly across Venus's entire atmosphere. They arrived at specific locations determined by Venus's position during the encounter. On November 3rd, Venus's orbital geometry placed the arrival point in late morning solar time. The region was sunlit, actively heated, experiencing upwelling circulation. As materials entered Venus's outer atmosphere, the thermosphere above 100 kilometers altitude, atmospheric drag began decelerating them. Light molecules, like water vapor and hydrogen cyanide moving at high velocities, penetrated deeper before atmospheric friction fully captured them. Heavier particles, Dust grains bearing nickel silicates and other minerals experienced stronger drag and decelerated faster, settling into the upper atmospheric layers without reaching the deeper cloud regions. This natural stratification meant different materials accumulated at different altitudes based on mass and aerodynamic properties. The result, a vertically layered deposition where the composition varied with altitude. Once materials reached the cloud layers, 45 to 70 kilometers altitude, they'd lost most of their original velocity. They were no longer incoming projectiles. They were now part of Venus's atmospheric system, subject to Venus's circulation. And Venus's circulation is extraordinary. Despite the planet's incredibly slow rotation, the atmosphere exhibits superrotation.
Winds at cloud level reach 100 meters per second, driven by solar heating pressure gradients and atmospheric wave dynamics that remain incompletely understood. This superrotation circles the entire planet in 4 days. Materials introduced at any specific location don't remain localized. Within hours, horizontal winds carry them hundreds or thousands of kilometers around the planet. Simultaneously, vertical circulation patterns, primarily the Hadley cell, where warm air rises at the equator and descends at higher latitudes, transport materials up or down through the cloud layers. The combination creates three-dimensional mixing. Over days to weeks, incoming materials are distributed throughout the atmospheric volume, though not uniformly. Downwelling zones where air descends can concentrate materials. Polar regions, where atmospheric dynamics are complex and somewhat isolated from the main circulation, might retain localized pockets of elevated concentrations.
But the key point is this: the materials weren't deposited and forgotten. They were captured, integrated, and immediately began circulating through an active dynamic system. And the moment they integrated into the sulfuric acid clouds, chemistry began. Venus's clouds are not passive containers, they're reactive environments. Sulfuric acid is one of chemistry's most aggressive compounds. It attacks organic molecules, strips electrons, breaks bonds, and transforms whatever enters into simpler components or acid-stable products. Or so we thought. Water mixing with sulfuric acid dilutes the acid locally. A droplet with 90% acid concentration encountering water vapor becomes 80%, then 70%, then 60% as more water dissolves. This dilution matters enormously for chemistry. Many reactions that proceed readily in dilute acid are suppressed in concentrated acid. Dilution opens pathways. Hydrogen cyanide dissolving in sulfuric acid undergoes hydrolysis reaction with water molecules in the acid solution. The products are ammonia and formic acid. This is established chemistry proceeding reliably under these conditions. But here's where it gets interesting. Ammonia is a base. In an overwhelmingly acidic environment, bases neutralize acid. They create micro-environments within droplets where pH rises, acidity decreases, and chemistry that couldn't occur in pure sulfuric acid becomes possible. These neutralized zones become reaction vessels within the larger acid droplet, small regions where the chemical environment is less aggressive, where organic molecules can persist longer, where synthesis reactions can proceed without being immediately destroyed by acid attack. Nickel arriving at Venus doesn't remain as metallic particles. Nickel reacts with sulfuric acid, forming nickel sulfate, a soluble compound that dissolves into the liquid phase. Those droplets now contain nickel ions, and nickel ions are catalysts. Even trace amounts of catalytic metals can accelerate specific reactions by factors of hundreds or thousands. Nickel catalyzes the water-gas shift reaction carbon monoxide plus water producing carbon dioxide plus hydrogen. It catalyzes Fischer-Tropsch reactions that build longer carbon chains from simple precursors. It facilitates peptide bond formation between amino acids. Venus's sulfuric acid droplets just acquired catalytic capabilities they've never possessed. The chemistry began immediately. not over geological timescales, not waiting for excavation or heating or technological intervention, immediately upon arrival. Within the first hours, water-diluted acid concentrations in the upper cloud layer, hydrogen cyanide began hydrating into ammonia and formic acid. Nickel dissolved into droplets and acquired catalytic roles. Atmospheric circulation started distributing everything horizontally and vertically. Within the first days, materials reached global distribution in the upper atmosphere. Photochemistry, driven by solar ultraviolet radiation, began breaking down molecules, creating reactive radicals, driving secondary reactions. Within weeks, where we are now in late November 2025, the perturbation has fully integrated into Venus's atmospheric system. The chemistry is active, exploring, transforming. Unlike Mars, where the interesting transformations require future robotic intervention, Venus needed nothing external. The planetary system itself immediately began processing the delivery. But what exactly is it processing? What chemistry arrived at Venus, and more importantly, what is Venus doing with it? To answer that, we need to examine something that should be impossible. We need to discuss how life's building blocks can survive in battery acid. The conventional wisdom was clear. Sulfuric acid destroys organic molecules. This isn't speculation. It's established chemistry verified in thousands of laboratory experiments over centuries. Sulfuric acid is so aggressive that chemists use it to break down complex materials into simpler components. It's how we digest tissue samples for elemental analysis. It's how we decompose organic matter industrially. Venus's clouds with sulfuric acid concentrations reaching 90% should be the ultimate destroyer. Organic molecules arriving there should last seconds or minutes before being torn apart. For decades, this assumption shaped how we thought about Venus's habitability, or rather, its absolute lack thereof. If organic chemistry can't survive in Venus's clouds, then the clouds can't support any chemistry relevant to life. Venus became the exemplar of uninhabitable, and we moved on to studying more promising targets, like Mars or the icy moons of the outer solar system.
Then, in March 2024, a team of researchers published a study in the journal Astrobiology that changed the paradigm. The study was straightforward. Take 20 biogenic amino acids, the exact molecules that form proteins in all Earth life. Subject them to sulfuric acid solutions matching Venus's cloud conditions. The concentrations matched what we measure in Venus's upper and middle cloud layers. The temperatures matched 0 to negative 40 degrees Celsius. The exposure times matched hours to days. The hypothesis was that most or all of these amino acids would degrade significantly or completely. That's what chemistry textbooks suggested. That's what experience with sulfuric acid indicated. The results told a different story. 11 amino acids showed complete stability. No reaction, no degradation. They remained intact, unchanged, even after extended exposure to sulfuric acid at Venus-like conditions. Glycine, alanine, valine, leucine, isoleucine, proline, phenylalanine, methionine, and others, the fundamental building blocks of proteins, survived. 8 additional amino acids showed stability even after undergoing partial chemical alteration. They transformed into related compounds, but didn't decompose into unrecognizable fragments. The carbon backbone remained. The functional groups were modified but not eliminated. Only 1 amino acid out of 20 showed significant instability and breakdown in these conditions. 19 out of 20, either completely surviving or surviving in recognizable altered forms. This finding demolishes the assumption that Venus's sulfuric acid instantly sterilizes all organic chemistry. It doesn't. Sulfuric acid is selective. It attacks certain molecular structures, hydroxyl groups, some amine configurations, certain aromatic systems, while leaving others essentially untouched.
The amino acids that survived possess structural features that resist acid attack. Compact geometries, stable chemical groups, configurations that don't present vulnerable sites for the acid to cleave. What this means is profound. The building blocks of life as we know it can persist in Venus's clouds, not for seconds, not for minutes, for days, possibly weeks depending on location and conditions. This completely changes how we think about what Venus received on November 3rd. Hydrogen cyanide breaks down in water to form amino acids. This is established prebiotic chemistry demonstrated extensively in laboratory experiments. When HCN dissolves in water under the right conditions, often requiring some energy input or catalysis, it polymerizes and transforms into amino acids and other organic compounds. The HCN delivered by 3I Atlas doesn't arrive as stable inert molecules. It arrives reactive, ready to transform. When it encounters the dilute sulfuric acid in Venus's upper clouds, it begins hydrating immediately. The products of this hydration are exactly the types of amino acids the 2024 study showed can survive in sulfuric acid. The chemistry arriving at Venus includes precursors that transform into products that can persist. Let me walk through this more carefully, because it's the crux of why Venus's response to 3I Atlas is so remarkable. Hydrogen cyanide dissolves in the aqueous component of sulfuric acid droplets. Venus's clouds contain substantial water. The acid is dissolved in water, not pure anhydrous acid. The HCN encounters water molecules and begins hydrolyzing. The simplest pathway produces formamide, then formic acid and ammonia. But in the presence of multiple HCN molecules and sufficient energy provided by solar UV radiation constantly bathing the upper atmosphere, more complex pathways open. Amino acids synthesize through well-characterized reaction sequences.
Glycine, the simplest amino acid, forms readily. Alanine, the next simplest, follows. More complex amino acids require more steps, but the chemical pathways exist and proceed under these conditions. And once formed, these amino acids don't immediately decompose. They persist in the sulfuric acid environment. The 2024 study confirmed they can survive for extended periods. But it's not just survival. The ammonia produced alongside the amino acids serves a critical function. Ammonia in acid-base chemistry is a base. When it forms in a sulfuric acid droplet, it doesn't simply float around. It reacts with the acid, neutralizing it locally. The chemical reaction is straightforward. Ammonia plus sulfuric acid produces ammonium sulfate and water. Ammonium sulfate is a salt-neutral pH, neither acidic nor basic. Within the droplet regions where ammonia has neutralized the acid become environments where pH is elevated, less acidic, more hospitable to organic chemistry. These microenvironments within the larger acid droplet become chemical sanctuaries, small zones where molecules can interact without being attacked by concentrated acid, where synthesis reactions can proceed, where complexity can build. The droplets become stratified. The bulk acid remains aggressive, but pockets within the droplet regions, enriched with ammonia and its products, create conditions where organic chemistry can be active. And there are billions of these droplets, billions of tiny chemical experiments, each slightly different in composition, temperature, and exposure to radiation, each exploring slightly different reaction pathways, each potentially stumbling onto pathways that produce unexpected products. Most droplets will produce nothing of particular interest, random combinations of molecules that don't lead anywhere chemically significant. But chemistry is a numbers game. With enough parallel experiments, even low-probability outcomes occur somewhere.
Venus's upper atmosphere is now running this experiment at massive scale, billions of droplets enriched with comet-delivered materials, each droplet containing amino acid precursors, water, dilute sulfuric acid trace, nickel compounds, and energy input from solar radiation. The chemistry isn't just surviving, it's active, exploring, building. This is not biology. This is not life. These are not living cells or organisms, but it represents complexity chemical structures more sophisticated than simple precursors, exhibiting organization and patterns that don't occur in random chemical mixtures. It's the kind of chemistry that astrobiologists study when trying to understand how life's building blocks could have emerged from non-living chemistry on early Earth. And it's happening right now. In Venus's clouds, not as some hypothetical future scenario, as active ongoing chemistry that began November 3rd and continues today. The amino acids are present. The conditions allow their persistence. The droplets provide reaction vessels. Solar energy drives transformations. And there's one more ingredient that makes this particularly remarkable: nickel, catalytic nickel. The refined metal delivered by 3I Atlas, because amino acids persisting is one thing. Amino acids linking together into larger structures, peptides, the precursors to proteins, requires overcoming energy barriers that don't easily break down spontaneously. Unless there's a catalyst, unless there's something accelerating the reaction, providing an alternative pathway, making the difficult chemistry possible. Venus just received exactly that catalyst from an interstellar comet, 10 billion years old, carrying metals refined through processes we don't fully understand. The implications are staggering, and to grasp them fully, we need to understand what catalysis is and why nickel's presence in Venus's clouds changes everything about what chemical complexity might emerge.
There's a reason life uses metals. Every living cell on Earth relies on metallic catalysts embedded in enzymes. Iron and hemoglobin carrying oxygen through your bloodstream. Magnesium at the heart of chlorophyll enabling photosynthesis. Zinc facilitating thousands of enzymatic reactions. Copper, manganese, molybdenum. The periodic table's transition metals are essential to biology, not as structural materials, but as catalysts. Catalysts work by providing alternative reaction pathways that require less activation energy than the uncatalyzed reaction. Think of a chemical reaction as a journey over a mountain. Reactants start in one valley. Products sit in another valley on the far side. The uncatalyzed reaction requires climbing over the mountain-high energy barrier. Slow progress, few molecules make it. A catalyst is like a tunnel through the mountain. Same starting point, same destination, but lower energy barrier. More molecules make the journey. The reaction proceeds faster. Orders of magnitude faster in many cases. The catalyst doesn't change whether a reaction is thermodynamically favorable, whether products are more stable than reactants. It changes how quickly the system reaches equilibrium. In systems where reactions are thermodynamically favorable but kinetically hindered, catalysts transform impossible into practical. Nickel is one of nature's most versatile catalysts. It's used industrially in hydrogenation reactions, where hydrogen atoms are added to organic molecules. It catalyzes the formation of carbon-carbon bonds. It facilitates the water-gas shift reaction. And critically, nickel-containing enzymes in living organisms catalyze some of biology's most essential reactions. Urease, the enzyme that breaks down urea, uses nickel at its active site. Hydrogenase enzymes that process molecular hydrogen rely on nickel. Methyl coenzyme M reductase, essential to methanogenic archaea producing methane, is a nickel enzyme. Biology discovered early that nickel could facilitate reactions difficult to achieve otherwise. And now, Venus's atmosphere contains dissolved nickel ions for the first time in its history. When nickel from 3I Atlas encounters sulfuric acid in Venus's clouds, it doesn't remain as metallic particles. Nickel metal reacts with acid nickel, plus sulfuric acid produces nickel sulfate, plus hydrogen gas. Nickel sulfate is soluble. It dissolves into the liquid phase of the droplets. Those droplets now contain nickel ions positively charged, nickel atoms surrounded by water molecules, and sulfate ions. These ions are catalytically active. They can coordinate with organic molecules, bringing them into proximity.
stabilizing transition states, facilitating bond formation or breaking. The water-gas shift reaction becomes viable in Venus's clouds for the first time. Carbon monoxide plus water producing carbon dioxide plus hydrogen. Under normal circumstances, this reaction proceeds slowly at Venus's cloud temperatures. The activation energy is too high. But nickel catalyzes it. Nickel provides a surface where CO and water molecules can adsorb adjacent to each other. The metal facilitates electron transfer. The reaction proceeds. Products release, and the nickel is ready to catalyze the next reaction. The significance isn't immediately obvious until you consider the products. Hydrogen produced through this reaction is the lightest molecule in chemistry. If it reaches high enough altitudes, it can escape Venus's gravity entirely lost to space. Hydrogen escaping represents a net loss of atmospheric mass, tiny on individual reaction scales, but potentially measurable if the catalyzed reaction proceeds extensively. But before hydrogen escapes, it's available for other reactions. Hydrogen is a reducing agent. It donates electrons. Sulfuric acid can be reduced by hydrogen producing sulfur dioxide and water. Organic molecules can be reduced, altering their structures, producing different compounds with different properties. The presence of hydrogen creates reducing conditions in localized regions of the droplet's microenvironments, where the chemistry is fundamentally different from the oxidizing conditions that dominate Venus's atmosphere. Fischer-Tropsch reactions become possible. These are processes where carbon monoxide and hydrogen combine to form longer-chain hydrocarbons and organic molecules. Industrially, Fischer-Tropsch requires high temperatures and pressures along with metal catalysts, iron or cobalt typically, but nickel works. Venus's clouds aren't ideal Fischer-Tropsch conditions. Temperatures are too low. Pressures, while high for an atmosphere, are lower than industrial reactors, but chemistry doesn't require ideal conditions to proceed. It requires sufficient conditions.
And in droplets, where nickel concentration is elevated, where CO and hydrogen are present from the water-gas shift, where local temperatures happen to be favorable, the reaction might proceed. Even at very low rates, Fischer-Tropsch would produce molecules Venus's atmosphere doesn't normally contain. Longer-chain organics. Molecules with multiple carbon atoms bonded together. Structures more complex than the simple precursors delivered by the comet. Beyond these specific named reactions, nickel catalyzes general organic condensation reactions. If amino acids are present in a droplet, and we've established they can be present and stable, nickel can facilitate peptide bond formation. Peptide bonds are what link amino acids together into chains. 2 amino acids bonding form a dipeptide. 3 form a tripeptide. Longer chains form polypeptides and eventually proteins. The reaction requires removing a water molecule dehydration synthesis. It's energetically unfavorable without help.
Enzymes in living cells catalyze this constantly building proteins from amino acid sequences. Venus's clouds don't have enzymes, but they now have nickel ions. If 2 amino acids dissolved in the same droplet encounter a nickel ion, the metal can bring them together, stabilize the transition state where the peptide bond forms, and facilitate the reaction. The resulting dipeptide remains in solution. It might encounter another amino acid and nickel ion forming a tripeptide. The process can continue. We're not talking about synthesizing functional proteins. We're discussing whether amino acids can link into short chains 2, 3, 4 amino acids long. Even these short peptides represent complexity beyond the simple monomers. They're oligomers' early steps toward the polymers that life uses. The concentration of nickel in Venus's clouds, after 3I Atlas's delivery, is estimated at parts per billion levels, extraordinarily low. But biological systems operate at similar concentrations for many essential elements. Enzymes in cells are typically present at parts per million to parts per billion.
The key is turnover number, how many reactions a single catalyst molecule facilitates before being deactivated. Enzymes often have turnover numbers in the thousands or millions. One enzyme molecule catalyzing thousands of reactions per second. Nickel in Venus's clouds won't match enzymatic efficiency, but it doesn't need to. It just needs to be active. One nickel ion dissolved in a droplet can facilitate multiple reactions over the weeks. It remains in that environment before the droplet precipitates or the nickel reacts into an unreactive form. Multiply that by billions of droplets containing some nickel each running chemical experiments over weeks, and the total number of catalyzed reactions becomes substantial. The question is whether nickel catalysis actually produces measurable increases in chemical complexity. The theoretical answer is yes. The practical answer depends on factors we don't yet know precisely. The exact concentration of nickel in droplets, the local concentrations of reactant molecules, the temperature profiles droplets experience as they circulate through different altitudes, the residence time of nickel in catalytically active forms. These are parameters the data from Japan's Akatsuki orbiter might reveal, or parameters modeling studies can estimate. But the mechanism is sound. The chemistry is real. Nickel is present. The conditions allow catalysis. What makes this parallel to biology so fascinating is that life didn't invent catalysis. Life discovered it. Early in Earth's history, before life existed, chemical systems incorporating metal ions from the environment would have experienced catalytic acceleration of certain reactions. Systems that happen to incorporate effective catalysts would explore chemical space faster, build complexity more efficiently, perhaps stumble onto self-sustaining reaction networks that resembled metabolism. Origin of life research focuses heavily on this period, the prebiotic chemistry phase, where non-living systems explored reaction pathways that eventually, through processes we still don't fully understand, crossed the threshold into biology. Venus's clouds are now engaged in a version of that exploration. Not biological, not guided, not intentional, but catalytic. And catalysis is one of the key mechanisms that separates complex chemistry from random molecular combinations. Venus's atmospheric chemistry was already interesting because the organic precursors delivered by the comet can survive in sulfuric acid. Add catalysis, and it becomes more interesting still. The chemistry isn't just surviving. It's being accelerated, organized, pushed toward complexity at rates faster than thermal processes alone would allow. Each sulfuric acid droplet circulating through Venus's upper atmosphere is a tiny experiment, testing whether catalytic nickel can drive reactions producing unexpected products. Most experiments will yield null results. But with billions of parallel experiments running for weeks, even low probability outcomes occur somewhere. The outcome is unknown. We're inferring what must be happening based on chemistry we understand and materials we know arrived. But the framework is clear. Venus's clouds are enriched with catalytic nickel prebiotic organic molecules and energy input from solar radiation. Those are ingredients for complexity. Whether complexity actually emerges at detectable levels is what observation will tell us. But the possibility exists, and that possibility is being explored right now in Venus's atmosphere, whether we're watching or not.
The chemistry doesn't wait for our instruments or papers. It proceeds according to its own rules. And those rules now include catalysis provided by nickel from an interstellar comet. That's the gift 3I Atlas gave Venus, not just raw materials, but the tools to build with them. If we could descend through Venus's atmosphere with instruments sensitive enough to map chemistry in real time, we'd discover that Venus's clouds are not uniform. What appears from orbit as a continuous layer is actually 3 distinct chemical zones, each operating under different conditions, each hosting different reactions, each responding differently to the materials 3I Atlas delivered. The upper cloud layer, 60 to 70 kilometers altitude, is where the comet's delivery first made contact. Here, sulfuric acid concentrations are relatively dilute, 50 to 75%, mixed with substantial water. Temperatures hover around 0 to -20 degrees Celsius. Cold. Cold enough that water can condense into ice crystals at the highest reaches. Cold enough that certain organic molecules remain stable longer before photochemistry breaks them down. Atmospheric pressure at these altitudes is low, roughly 1/10 of Earth's surface pressure. Molecules have longer mean free paths between collisions. Lower collision frequency means slower reaction rates. This is beneficial for preservation. Molecules persist longer when they're not constantly colliding and reacting. The upper cloud layer is also where atmospheric mixing is most vigorous. Winds driven by temperature gradients and pressure differences create circulation patterns, redistributing atmospheric contents around the planet every 4 days. Materials arriving here don't stay localized. They're immediately caught in global circulation. Light molecules, water vapor, hydrogen cyanide, gas, carbon monoxide penetrate through this layer relatively easily. They're moving fast when they arrive, and the thin density doesn't decelerate them quickly. These molecules continue downward toward the middle cloud layer. Heavy particles, dust grains bearing nickel silicates. Organic macromolecules decelerate faster. Higher mass means more momentum to shed. Larger surface area means more atmospheric drag. These particles settle into the upper cloud layer and remain there longer before eventually precipitating downward. The result is spatial separation. Light molecules concentrate in lower layers initially, while heavy particles concentrate in upper layers. Over time, vertical circulation mixes things, but during the first days after arrival, this stratification is pronounced. Descending to 50 to 60 kilometers, we enter the middle cloud layer. Sulfuric acid concentrations increase to 75 to 90%. Water content decreases. Temperatures drop further, -20 to -40 Celsius. This is the region where most visible atmospheric features occur. The Y-shaped patterns in Venus's clouds, the vortices and waves that spacecraft cameras capture form in the middle cloud layer. It's denser than the upper layer. Droplets are smaller, more numerous, more concentrated. Chemistry here is more aggressive. Acid concentrations are high enough to attack molecules that survive the upper layer. Organic molecules that remained stable in dilute acid begin breaking down in concentrated acid. But the process isn't instant. It's faster than in the upper layer, but still measured in hours to days depending on molecular structure. Hydrogen cyanide reaching this layer continues its transformation. The hydrolysis reaction HCN breaking down into ammonia and formic acid proceeds more rapidly in the presence of water, and there's still water in these clouds, despite the high acid concentration. Ammonia formation creates basic microenvironments within droplets locally neutralizing acid. Nickel compounds, whether arriving as dust or dissolved from particles settling through, accumulate in droplets here. The catalytic reactions we discussed, water-gas shift. Fischer-Tropsch beginnings. Peptide bond formation proceed most actively in this middle layer. Temperatures are cold enough to stabilize intermediates, but warm enough for reactions to proceed at meaningful rates. Acid concentration is high enough to provide a dense reactive medium, but not so high that everything is immediately destroyed. The middle cloud layer is Venus's chemical sweet spot for the processes we're discussing. Below that 45 to 50 kilometers altitude lies the lower cloud layer. Sulfuric acid concentrations reach their peak, 80 to 90%. Temperatures rise -40 to -60 Celsius. Pressure approaches 1 Earth atmosphere. This is the terminal zone for most organic chemistry. Molecules that survive the upper and middle layers encounter conditions here that overwhelm them. High acid concentration, elevated temperature, long residence time. Most complex organics break down into simpler components: carbon dioxide, water, Sulfur dioxide, simple nitrogen compounds. The building blocks return to their constituent parts. Some are absorbed into the droplets and precipitate further downward. Others, being gases, rise back up through convection, recycled into the upper layers to begin the cycle again. The lower cloud layer acts as a chemical filter. Only the most stable compounds, carbon dioxide, nitrogen, noble gases, pass through unscathed. Everything else transforms or is destroyed. Beneath all three cloud layers, 0 to 45 kilometers altitude, lies what's optimistically called the clear atmosphere. The region is clearer than the clouds above, but far from transparent. Hazes and aerosols scatter light. The atmosphere here is dominated by carbon dioxide and nitrogen, with temperatures increasing dramatically toward the surface. No complex chemistry survives down here. By the time you approach Venus's surface, temperatures exceed 400 degrees. Organic molecules decompose, metals oxidize. Even water breaks apart into hydrogen and oxygen. This is Venus's crematorium, where everything complex returns to simple forms. The delivery from 3I Atlas never penetrated this deep. The materials that arrived were captured in the cloud layers 45 kilometers and above. That's where the story is unfolding. But understanding the layering is critical, because different materials ended up in different zones. Water vapor, being light and moving fast, penetrated deepest initially before atmospheric drag captured it. Some water made it through the upper cloud layer, entirely arriving in the middle layer where acid concentrations are highest. This water immediately began diluting the acid, locally releasing heat through the exothermic reaction of water mixing with concentrated acid. Hydrogen cyanide, slightly heavier than water, but still gaseous, similarly penetrated into the middle cloud layer. Here, it began hydrating, most rapidly producing ammonia and formic acid in the concentrated acid environment. The ammonia generated created the neutralized microenvironments we discussed. Carbon monoxide with a molecular weight similar to nitrogen distributed fairly uniformly through all three cloud layers. It's relatively inert in purely acid conditions, but in the presence of nickel catalyst and hydrogen from the water gas shift, it becomes reactive. Nickel-bearing dust grains, heavy and irregular in shape, decelerated quickly in the upper cloud layer. Some particles remained suspended there. Others, through collision and agglomeration, grew large enough to begin precipitating slowly downward. As they descended, they passed through increasingly concentrated acid. The nickel reacted, dissolved, and distributed its catalytic capacity throughout the cloud system. By late November, several weeks after the encounter, vertical and horizontal circulation has mixed materials extensively. The initial stratification has blurred. Nickel that started in the upper layer has been transported downward and upward by convective circulation. Water that arrived in the middle layer has been carried upward by rising air and downward by precipitation. The cloud system has become a more homogeneous mixture, though concentration gradients still exist. Regions of downwelling, where air descends from the upper atmosphere, have accumulated higher concentrations of materials. Polar vortices, where atmospheric dynamics create isolated circulation patterns, may retain pockets of elevated chemistry. Observing these patterns requires spacecraft instruments capable of mapping atmospheric composition with altitude and location. Spectrometers that can measure trace gas concentrations. Particle sensors that can determine cloud droplet composition. Imaging systems that can track how atmospheric features evolve. Japan's Akatsuki orbiter carries these instruments. During the November 3rd encounter and the weeks following, Akatsuki observed Venus's atmosphere continuously. The data it collected should reveal whether the patterns we're describing actually occurred. If water vapor concentrations in the middle cloud layer elevated temporarily after November 3rd, Akatsuki's infrared spectrometer would detect it. If hydrogen cyanide or carbon monoxide signatures appeared where they shouldn't, spectroscopic analysis would capture them. If cloud droplet sizes or compositions changed, particle sensors would register the shift. The data exists. The analysis is ongoing, and within months we'll know whether Venus's stratified cloud system responded to 3I Atlas's delivery in the ways chemistry predicts. But regardless of what observation confirms, the framework is clear. Venus's clouds are not a uniform chemical environment. They're a vertically stratified system where temperature, pressure, and composition vary dramatically with altitude. Materials arriving from the comet encountered all three layers simultaneously, but were distributed according to their physical properties. Light molecules went deep, heavy particles stayed high. Each found itself in a different chemical regime, experiencing different reaction conditions following different transformation pathways. The complexity of Venus's atmospheric structure creates complexity in chemical response. Different zones exploring different reactions, different altitudes hosting different concentrations. The system as a whole becoming a multi-layered experiment in what happens when interstellar chemistry meets planetary acid. And now, with that structure understood, we can ask the crucial question, what is actually happening? What chemical transformations are proceeding right now in Venus's clouds? What products are forming? What complexity is emerging? This is not archaeology. This is not paleochemistry, preserved in ice waiting for excavation and analysis. This is active transformation happening right now while you're listening to these words. Venus's atmosphere is processing the materials 3I Atlas delivered, and that processing is measurable, dynamic, and ongoing. Let me walk you through what's unfolding in real time above a world that hasn't experienced external chemical input in billions of years. In the first hours after November 3rd, water from the comet mixed with sulfuric acid throughout the cloud layers. The reaction is violent in microscopic terms. Water molecules encounter concentrated acid. The acid's affinity for water is so strong that energy releases as heat. The droplets warm slightly. The warming accelerates other reactions, but more importantly, the dilution changes everything. A droplet that was 90% acid becomes 80%, then 70% as more water dissolves. Chemical properties shift. Molecules that would be protonated and destroyed in 90% acid can survive in 70% acid. The dilution creates conditions in the upper and middle cloud layers that are genuinely different from Venus's normal state, less aggressive, more hospitable to organic chemistry. This window of opportunity, diluted acid before the water is fully absorbed and dispersed, lasts for days to weeks, depending on atmospheric circulation. During this window, hydrogen cyanide transformation accelerates. HCN hydrating into ammonia and formic acid proceeds rapidly in the presence of water. The ammonia generated doesn't float freely. It immediately reacts with sulfuric acid, neutralizing it too. Ammonia molecules plus one sulfuric acid molecule produce ammonium sulfate plus water. Ammonium sulfate is a salt, neutral. Neither acidic nor basic. Within the droplets regions where ammonia has formed and neutralized acid become chemical sanctuaries. The pH in these micro-regions rises dramatically, from perhaps -1 or 0 in pure concentrated sulfuric acid to potentially 5 or 6 in the neutralized zones. This pH change opens reaction pathways that don't exist in pure acid. Amino acid synthesis from HCN proceeds more readily at elevated pH. Peptide bond formation between amino acids doesn't require as much activation energy. Organic condensation reactions that build complexity become favorable. The neutralized zones don't last forever. Eventually, the ammonium sulfate itself may decompose or be transported out of the droplet through evaporation and condensation cycles. But for days to weeks, these sanctuaries exist, hosting chemistry that Venus's normal acid environment suppresses. Simultaneously, nickel ions dissolved from dust grains begin their catalytic work. The water-gas shift reaction starts proceeding, carbon monoxide plus water producing carbon dioxide plus hydrogen. This reaction has two critical effects. First, it consumes carbon monoxide. CO concentrations in the enriched regions begin declining. Carbon dioxide concentrations rise. Venus's atmosphere is already 96% carbon dioxide, so the additional CO2 doesn't matter much. But the CO depletion creates a concentration gradient. More CO diffuses in from surrounding atmosphere. The reaction continues as long as nickel catalyst and water are present. Second, the reaction produces hydrogen, molecular hydrogen, H2. The lightest molecule in chemistry. Hydrogen doesn't stay in the liquid phase of droplets easily. It escapes into the gas phase. It rises through the atmosphere. If it reaches altitudes above 100 kilometers, where atmospheric density drops dramatically, some fraction escapes Venus's gravity, entirely lost to space. But the hydrogen that doesn't escape immediately is available for reduction reactions. Sulfuric acid exposed to hydrogen in the presence of metal catalysts can be reduced sulfuric acid plus hydrogen producing sulfur dioxide plus water. This reaction consumes acid. It generates more water. It further dilutes the droplets. A feedback loop emerges. Water dilutes acid. Dilute acid allows HCN hydration and ammonia formation. Ammonia neutralizes more acid. Nickel catalyzes water gas shift producing hydrogen. Hydrogen reduces acid producing more water. The cycle reinforces itself, pushing the droplet's chemistry away from the normal Venusian state towards something more neutral, more water-rich, more hospitable. This doesn't happen in all droplets, only those that captured sufficient concentrations of the delivered materials. Only those where nickel concentration reached catalytically active levels. Only those where ammonia production was high enough to neutralize local acidity. But across billions of droplets in Venus's upper atmosphere, some fraction, perhaps 1 in 1,000, perhaps 1 in 1,000,000, we don't know, entered this feedback cycle and began exploring chemical territory Venus doesn't normally access. Photochemistry complicates everything. Solar ultraviolet radiation constantly bombards Venus's upper atmosphere. UV photons carry enough energy to break chemical bonds. Water molecules photodissociate into hydrogen and oxygen atoms. Hydrogen cyanide breaks down into cyanide radicals and hydrogen atoms. Ammonia decomposes into nitrogen and hydrogen. Photodissociation is destructive. It tears apart the complex molecules, returning them to simpler fragments. This is the ultimate cleanup mechanism that will eventually eliminate the comet-delivered materials entirely. But photodissociation creates intermediates, radical species that are highly reactive. These radicals don't simply float away. They react with other atmospheric molecules, forming new compounds. Hydrogen atoms from water photolysis can react with carbon dioxide, forming formic acid. Oxygen atoms can react with carbon monoxide, forming carbon dioxide. Cyanide radicals can react with ammonia, forming more complex nitrogen-bearing organics. The photochemistry drives a cascade. Original molecules break down, but their fragments recombine, creating products that are themselves substrates for further reactions. The system doesn't simply degrade monotonically towards simple components. It explores a network of transformations. Some pathways lead to increased complexity, radicals coupling together, forming bonds, building larger molecules. Other pathways lead to simplification, breaking bonds, producing volatile fragments that escape into the gas phase. The balance between construction and destruction determines what survives. And that balance depends on local conditions, temperature, pressure, radiation intensity, reactant concentrations, catalyst availability. In the upper cloud layer, where UV intensity is highest and acid is most dilute, photodestruction dominates. Molecules break down faster than synthesis can rebuild them. This layer is hostile to complexity, despite the favorable acid concentration. In the middle cloud layer, deeper below the UV-absorbing haze, photochemistry is less intense. Synthesis reactions have more time to proceed before UV breaks the products apart. This is where complexity has the best chance of emerging and persisting.
In the lower cloud layer, acid concentration and temperature become limiting factors. Molecules that might survive photochemistry in the middle layer get destroyed by chemical attack in the lower layer. There's a sweet spot, middle cloud layer. Moderate acid concentration. Reduced UV intensity. Sufficient catalyst and reactant concentrations. If chemical complexity beyond simple amino acids is forming in Venus's atmosphere right now, it's forming there. What would that complexity look like? Not proteins, not functional enzymes, not anything approaching biological sophistication, but perhaps dipeptides, two amino acids linked, perhaps oligopeptides, chains of 3 or 4 amino acids. Perhaps small organic molecules with multiple functional groups synthesized through reactions between HCN derivatives and other organics.
Perhaps molecules we wouldn't immediately recognize formed through pathways unique to Venus's sulfuric acid environment, not seen on Earth or in laboratory simulations. The time scale for these transformations is rapid compared to geological processes, but slow compared to human perception. Over the first week after November 3rd, initial reactions, water dilution, HCN hydration, nickel dissolution went to near completion in the affected droplets. Over the second and third weeks, secondary reactions, ammonia, neutralization, peptide formation, catalytic Fischer-Tropsch beginnings would have started if conditions were favorable. By now, late November 2025, we're 3 to 4 weeks out. Photochemistry has been breaking down the most vulnerable molecules continuously. Original HCN has been largely converted to products or destroyed. Original water has been absorbed into the acid-water equilibrium. Original carbon monoxide has been partially consumed by catalytic reactions.
But the products of those transformations, amino acids, ammonium compounds, reduced carbon species, oligomers may still be present in the droplets that created favorable conditions. The perturbation is fading. Venus's chemistry is gradually returning toward its normal state. Photochemistry eliminates foreign molecules. Circulation disperses concentrated regions. Precipitation removes materials from the atmosphere. By January or February 2026, most traces of the comet delivery will likely be gone, degraded, or dispersed below detection limits. But for this brief window, November through December 2025, possibly into early 2026, Venus's atmospheric chemistry is different, perturbed away from equilibrium, exploring reactions it doesn't normally access, testing whether the combination of interstellar organics, catalytic metals, and planetary atmospheric dynamics can generate complexity. The outcome is unknown. The predictions are preliminary. The observations haven't been fully analyzed yet, but the framework is clear and the chemistry is real. Somewhere in Venus's middle cloud layer, right now at roughly 55 kilometers altitude, there are droplets containing amino acids that survived sulfuric acid nickel ions catalyzing reactions and neutralized microenvironments where pH is elevated. Whether those droplets contain anything more complex, anything that would surprise us, anything that challenges our assumptions about where organic chemistry can operate, is the question the data will answer. But the experiment is running. Nature is conducting it. And we're in the waiting phase, the period between observation and understanding, where speculation gives way to measurement. Stay with me. Because to fully grasp what this means, we need to step back and look at the larger framework. We need to examine 3 different ways of interpreting what's happening at Venus. 3 hypotheses ranging from conservative to bold, each with different implications for how we think about planetary chemistry and the potential for complexity to emerge in extreme environments. Science advances through hypothesis testing. We observe phenomena, propose explanations, make predictions, and test those predictions against further observation. The process works best when we consider multiple competing hypotheses, simultaneously weighing evidence for and against each. For what's happening at Venus right now, three frameworks stand out. Each is scientifically grounded. Each makes different predictions. Each has different probabilities based on current understanding. And each implies something different about the universe's capacity to generate complexity. Let's examine them in order of decreasing probability and increasing boldness. Hypothesis 1, natural chemical enrichment, probability. High, scientific support strong, the conservative interpretation. 3I, Atlas past. Venus captured materials integrated into cloud layers. Chemistry proceeded according to established pathways. HCN hydrated into ammonia and formic acid. Water diluted acid. Nickel dissolved and catalyzed reactions. Amino acids formed through documented prebiotic routes. The 2024 study confirmed amino acid survival. Nickel catalysis accelerates reactions, but doesn't create fundamentally new chemistry. Photochemistry gradually breaks down organics over weeks to months. Result temporary enrichment. Interesting scientifically, but not transformative. Venus returns to equilibrium by early 2026. Hypothesis 2. Sustained complexity. Generation probability. Moderate to low. Speculative but chemically plausible. This moves beyond simple enrichment. The feedback loops water, diluting acid ammonia, neutralizing acid nickel. Catalyzing reactions producing more water might reinforce each other in favorable droplets. Where initial concentrations were sufficient, stable chemical cycles could emerge. Amino acids form more readily in neutralized zones. Nickel catalyzes peptide formation. Oligomers might persist for months in protected regions or polar vortices. Venus's clouds might contain pockets of organized complexity for extended periods, not life, but prebiotic reaction networks, exhibiting properties we associate with life's chemistry. Hypothesis 3. The atmospheric habitability. Question, probability. Low, highly speculative. The bold speculation connecting to long-standing proposals about life in Venus's clouds. If microbial life somehow exists, they're extremely unlikely it just received food. The chemistry present could support hypothetical metabolism. But this is not claiming life exists. The gap between complex chemistry and biology remains enormous. This hypothesis acknowledges that the chemistry now present could theoretically support life if organisms were there, which they almost certainly aren't. 3 hypotheses, 3 interpretations of the same event, 3 different implications for how we understand planetary chemistry. The data to discriminate between them exists, Akatsuki observed. Ground-based telescopes observed. The measurements were made. Now comes the analysis, the peer review, the publication, and the scientific debate. Within 6 months, we'll know which hypothesis aligns best with observation. Whether Venus experienced simple, temporary enrichment, whether complexity persisted beyond expectations, or whether something even more remarkable occurred. But here's what's important: regardless of which hypothesis is correct, we've learned something profound. We've learned that Venus, the planet we use as shorthand for uninhabitable, the exemplar of sterile hell, can receive chemistry from outside, process it in ways we're still working to understand, and at minimum, host amino acids in organic reactions we thought impossible there. The universe is more permissive than our assumptions. Chemistry is more creative than simplified models suggest. And planets respond to external inputs in ways that can surprise us, challenge our categories, and expand what we consider possible. That's the real discovery. Not whether specific molecules persisted or not, but recognizing that we've underestimated what Venus's clouds can do. And if we underestimated Venus, what else have we underestimated about where complex chemistry and perhaps life itself can operate?
There's a fundamental challenge in planetary science. We're trying to understand entire world's objects with trillions of tons of mass complex atmospheric dynamics. Global-scale processes using instruments we can only place in a few locations for limited time. Every observation is a narrow window. Every measurement captures one slice of a much larger system, and the confidence we can place in our conclusions depends critically on how many windows we have, how many independent observations we can compare. When 3I Atlas passed Mars on October 3rd, multiple spacecraft observed NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, China's Tianwen-1 orbiter. 3 independent platforms with different instruments, different orbital geometries, different observational capabilities. If one spacecraft detected something anomalous, others could verify or refute it. The redundancy created confidence. Venus, on November 3rd, was different. One spacecraft, Japan's Akatsuki orbiter, flying solo. Akatsuki is a capable mission.
Launched in 2010, it initially failed to enter Venus orbit but was successfully recovered 5 years later, arriving in 2015. Since then, it's been studying Venus's atmospheric dynamics, cloud patterns, and meteorology. The spacecraft carries 5 cameras operating at different wavelengths, from ultraviolet to infrared, allowing it to peer into different atmospheric layers. Specifically, Akatsuki carries UVI ultraviolet imager, observing cloud patterns in reflected UV light. IR1, 1-micron camera, penetrating clouds to sense thermal emission from lower atmosphere. IR2, 2-micron camera tracking sulfur dioxide and other gases through spectroscopy. LIR long-wave infrared, camera mapping temperature structure, LAC lightning, and air glow camera detecting atmospheric electrical activity and air glow. These instruments can detect changes in atmospheric composition, temperature, and cloud properties. If the comet's delivery altered Venus's atmosphere measurably, Akatsuki should see it. But should carries uncertainty. Instrument sensitivity matters. Every spectrometer has detection limits, minimum concentrations, below which signals are lost in noise. If HCN concentrations in Venus's clouds increased from parts per trillion to parts per billion, that's a 1,000-fold increase. Scientifically significant. But if the parts per billion level still falls below the instrument's detection threshold, Akatsuki won't see it. Coverage matters. Akatsuki is in an elliptical orbit around Venus with a period of about 10 Earth days. It's not continuously observing every part of Venus's atmosphere. It samples. If the comet delivered materials concentrated in specific atmospheric regions that Akatsuki didn't observe intensively during the critical period, the signal could be missed even if it was there. Timing matters. Some of the chemistry we've discussed proceeds over hours to days. If Akatsuki's observational campaign emphasized the wrong times, perhaps focusing on day-side when interesting night-side chemistry was occurring, or observing at wavelengths that couldn't detect the relevant species, critical evidence could go unrecorded. These aren't criticisms of the mission. Akatsuki wasn't designed specifically to catch interstellar comets delivering materials to Venus. It was designed for long-term atmospheric monitoring. That it was operating during the November 3rd encounter is fortunate. That it's the only spacecraft there is a limitation we have to acknowledge. The data downlink is complete by now, late November 2025. Transmission from Venus to Earth is slow bandwidth, limited by the spacecraft's power and transmitter capabilities. But over weeks, the observations have been radioed back to Japan's Institute of Space and Astronautical Science, received and stored. Now begins calibration. Raw instrument data isn't immediately scientifically usable. Electronic offsets need correction. Thermal drifts compensated. Cosmic ray hits removed. The data must be converted from voltages and counts into physical units, radiance, temperature, concentration. This work is tedious but essential. It's performed by mission scientists who've spent years understanding their instruments' quirks and behaviors. Rushing would introduce errors. Patience yields accuracy. By late December 2025, preliminary calibrated data will likely be available for scientific analysis. Not publicly released, yet first analysis happens internally, but ready for the mission team to examine. What they'll look for: temporal changes in atmospheric composition between pre-encounter, during encounter, and post-encounter observations. Spatial patterns showing elevated concentrations of water vapor, HCnCO or sulfur dioxide, in regions where comet material should have deposited spectroscopic signatures indicating unusual organic compounds or unexpected chemical species. Changes in cloud droplet properties, size, distribution, composition, optical thickness, consistent with external material incorporation. Thermal anomalies or circulation pattern changes suggesting atmospheric response to material injection. If signals appear in the data, the next phase is verification. Are these signals real or artifacts? Do they exceed instrumental noise? Are they statistically significant? This scrutiny is scientific rigor in action, preventing false positives from entering the literature. Assuming signals pass verification, scientific interpretation begins. What concentrations do the measurements imply? What chemical species are present? How do observations compare to model predictions? What do the results mean for understanding Venus's atmospheric chemistry? This analysis phase extends into January and February 2026. Multiple team members work independently, comparing results, resolving discrepancies. The goal is consensus, a shared understanding of what the data shows. Simultaneously, writing begins. Scientific papers must be crafted with care. Methods, results, discussion, conclusion. Figures showing data. Tables quantifying measurements. References to prior work. Everything documented so others can evaluate the claims. First paper submissions to journals likely occur in late February or March 2026, perhaps sooner if results are particularly dramatic and warrant rapid communication. Journal selection depends on findings, Nature or Science for major discoveries, Icarus or geophysical research letters for solid but incremental findings, Astrobiology if the implications touch on prebiotic chemistry. Peer review takes time, typically months. Reviewers, expert scientists working anonymously, evaluate the paper's methods, data, quality interpretation, and conclusions. They suggest revisions. Authors respond, revise, resubmit. The process iterates until reviewers are satisfied. Publication might occur June or July 2026 if everything proceeds efficiently. Could be delayed to August or September if reviews require substantial revisions. That's the timeline. Observation in November 2025, analysis through winter publication by mid-2026, about 7 to 8 months from encounter to public scientific documentation. For those following closely, preprint servers offer earlier access. The Archive preprint archive allows authors to post papers before formal peer review, making results immediately available to the scientific community and public. If researchers choose this route, preliminary findings could appear as early as January or February 2026, but preliminary means preliminary. Preprints haven't been peer-reviewed. They might contain errors corrected later. Interpreting them requires caution. The media will cover these findings. Science journalists will translate technical results into accessible language. Some coverage will be excellent, accurate, measured, contextualizing the findings appropriately. Some will sensationalize, perhaps overstating what was discovered or speculating beyond what data supports. That's the nature of science communication. The public hears about findings through this imperfect filter. Critical thinking is required. Does the headline match the actual paper content? Are journalists distinguishing between observed facts and speculative interpretations? Are extraordinary claims backed by extraordinary evidence for those interested in following this story as it develops? Here's what to watch.
Check arcs.org regularly for preprints tagged with Venus Akatsuki or 3i Atlas. Follow planetary science news sites. PlanetarySocietySpace.com, Astrobiology Magazine Monitor. Professional Astronomy Planetary Science Twitter accounts where researchers discuss new findings. Watch for press releases from JAXA about Akatsuki observations. Look for conference presentations. At meetings like the Lunar and Planetary Science Conference or Division for Planetary Sciences meetings. And remember, absence of evidence isn't evidence of absence. If Akatsuki data shows no significant chemical changes, it could mean Venus's response was minimal below detection limits, or that we're looking in the wrong places with the wrong tools. Null results are scientifically valuable but don't necessarily close the question. Conversely, positive detection of unusual chemistry doesn't immediately confirm the more speculative hypotheses. It confirms chemistry happened. Interpreting what that chemistry means requires additional work. Science is a process, not a product. The process takes time, proceeds carefully, and values accuracy over speed. The findings from Venus will emerge on science's schedule, not on the timeline of public curiosity. But the key point, the observations were made. The data exists. Analysis is underway. And within months, we'll have scientific documentation of what Venus's atmosphere looked like before, during, and after an interstellar comet's delivery of materials.
That documentation will constrain which hypotheses are viable and which must be abandoned. It will inform future research directions. It will teach us something about planetary atmospheric chemistry, regardless of specifics. And perhaps, if we're fortunate, it will surprise us. Science advances most rapidly when observations don't match expectations, when reality deviates from theory, when we're forced to reconsider assumptions. Venus has surprised us before. Soviet engineers expected landers to survive hours. Some failed in minutes. We expected runaway greenhouse effect to create uniform conditions. We found complex cloud-level dynamics. We expected sulfuric acid to sterilize all chemistry. Recent studies show amino acids survive. Maybe Venus has another surprise waiting in the Akatsuki data, or maybe it confirms what we predict. Either outcome advances understanding. For now, we wait, but we wait with anticipation, knowing the story continues whether we're watching or not.
The chemistry is real, the observations were made, the analysis proceeds, and science marches forward one careful measurement at a time, building understanding of how planets work and what they can do when touched by visitors from the stars. Long before telescopes, before spectroscopy, before spacecraft, humans watched Venus, not casually, obsessively, encoding its movements into their calendars, architecture, and mythology, tracking its cycles with precision that required generations of continuous observation. Why such attention to one bright point of light? Venus commands the sky when it appears. After the sun and moon, nothing in the heavens shines brighter. At maximum brilliance, Venus can cast shadows on moonless nights. Ancient peoples couldn't ignore it even if they wanted to. But brightness alone doesn't explain the obsession. The moon is bright. The sun dominates. Yet Venus received special treatment across cultures separated by oceans and millennia. Something about Venus's behavior captured human imagination in ways other celestial objects didn't. Perhaps it was the duality. Venus appears as the morning star before dawn, rising ahead of the sun, brilliant against the fading darkness. Then it vanishes for weeks or months, reappearing as the evening star after sunset, hanging in the western sky as twilight deepens. The Greeks initially thought these were two different objects. Phosphorus they called the morning appearance, the light bringer. Hesperus, the evening appearance, the evening star. Only later did they realize both were the same celestial body. Other cultures recognized the identity earlier. The Babylonians knew, the Maya knew, and they tracked Venus's movements with remarkable precision. The Maya particularly stand out. At Chichen Itza, the El Caracol Observatory's windows align with Venus's extreme positions on the horizon. At Uxmal, building orientations mark key Venus events. The Dresden Codex, one of the few surviving Maya books, contains Venus tables covering hundreds of years of the planet's synodic cycle. Venus's synodic period, the time between successive similar appearances as morning or evening star, is 584 days. The Maya knew this. They predicted Venus's positions centuries in advance. They developed correction factors to account for the slight discrepancy between the 584-day average and the actual period. Why such effort? What did Venus mean to them? In Maya cosmology, Venus was Kukulkan. In one aspect, the feathered serpent, a god of wind, rain, and life. Venus's appearances and disappearances marked important ceremonial times. Wars were timed to coincide with Venus's morning rising. Agricultural activities aligned with its cycles. Venus wasn't just an astronomical object to the Maya, it was integrated into their understanding of how the cosmos functioned, how time flowed, how human activities should synchronize with celestial patterns.
The Babylonians went further still. The tablet of Venus of Ammisaduqa, dating to approximately 1650 BCE, records 21 years of Venus observations during the reign of King Ammisaduqa. It documents when Venus appeared and disappeared, how long disappearances lasted, and what these events meant for omens. Babylonian astronomy was astrological. They tracked planets to predict earthly events. But the observations were meticulous. The data recorded in cuneiform on clay tablets is accurate enough that modern astronomers can use it to refine ancient chronologies. The Sumerians before the Babylonians identified Venus with Inanna, their most complex deity. Inanna was goddess of love and beauty, but also goddess of war and conflict. She embodied contradiction, creative and destructive, gentle and fierce, life-giving and death-dealing. This duality mirrors Venus's astronomical behavior, brilliant but transient, appearing and vanishing, morning brightness followed by evening brightness.
The planet itself seemed to embody the contradictions Inanna represented. Egyptian mythology associated Venus with two manifestations. Tiumutiri appeared in the morning. Waiti appeared in the evening. Eventually, they recognized both as the same, likely through contact with Mesopotamian astronomy, where this was already known. The Egyptians integrated Venus into their religious calendar, but with less intensity than the Maya. Venus wasn't their primary celestial focus. That honor belonged to Sirius, whose heliacal rising predicted the Nile's flood. But Venus still mattered. Its predictable cycles provided additional calendar markers. Its brightness made it impossible to ignore during appropriate seasons. Native American traditions treated Venus variously across cultures. Some Plains tribes saw Venus as a male warrior figure. Some Southwestern cultures associated it with twins, or duality given its morning-evening appearances. Pacific Northwest peoples incorporated Venus into creation myths. The common thread, Venus as important, as significant, as worth tracking, encoding into stories, passing knowledge to subsequent generations. What were these ancient observers really seeing? Astronomically, they were seeing a planet with an orbital period shorter than Earth's, creating complex apparent motions from our perspective. When Venus is on the far side of the Sun from Earth, it's visible after sunset. As it swings around toward passing between Earth and Sun, it disappears in solar glare. Then it emerges on the Sun's other side, visible before dawn. Then back around again. The 584-day cycle repeats. But at another level, they were seeing something else. They were observing a world that, unbeknownst to them, occasionally receives messages from beyond our solar system. A world that processes chemistry from interstellar space. A world in dialogue with the cosmos in ways they couldn't have imagined but perhaps intuited. The Maya described Venus as a messenger. In some myths, Venus carried communications between gods and the underworld. It traversed boundaries connecting realms. Metaphorically, they were right.
Venus does receive messages written not in glyphs or language, but in molecules, delivered by comets, meteorites, and dust from other parts of the galaxy, carrying information about stellar environments, interstellar chemistry, and processes operating on scales unimaginable to ancient peoples. The ancients couldn't have known Venus's surface temperature. They couldn't have known about sulfuric acid clouds. They certainly couldn't have predicted interstellar comets delivering prebiotic precursors. But they knew Venus was special. They devoted generations to tracking its movements. They wove it into their cosmologies as a figure of transformation, duality, and connection between different realms. In a sense, we're continuing their work. We're still watching Venus, still trying to understand what it means, still recognizing it as significant, worthy of attention, revealing something about the cosmos. Our tools are different: spacecraft instead of naked eye observation, spectrometry instead of mythology. But the impulse is the same: Venus matters. Venus teaches. Venus connects us to larger patterns. And now, for the first time, we're understanding one of those patterns. Venus doesn't just reflect sunlight for us to observe. Venus receives chemistry from the wider universe. It processes that chemistry. It responds according to its nature. The ancient Maya were right to see Venus as a messenger, even if they couldn't have understood the mechanism. Venus does carry information between different domains, not between gods and underworld, but between interstellar space and planetary atmospheres. Every culture that watched Venus was observing a laboratory,
a planetary-scale experiment in atmospheric chemistry, a world testing what happens when sulfuric acid clouds meet external inputs. They couldn't have articulated it that way, but they recognized something: Venus is not ordinary. Venus is not passive. Venus is dynamic, transformative, worthy of centuries of careful attention. We've now added one more chapter to that multi-millennial tradition of Venus observation. November 3rd, 2025, the day an interstellar comet delivered materials to Venus's atmosphere, the day ancient chemistry met modern observation. The ancients would probably appreciate the poetry of it. A messenger from deep time visiting the messenger planet, chemistry older than Earth arriving at Earth's twin. The cycles continuing, the patterns repeating, the cosmos demonstrating once again that Venus remains a world of transformation. And perhaps there's a lesson in how seriously ancient peoples took their Venus observations. They didn't have our technology, they couldn't measure atmospheric composition or track molecules. But they understood something fundamental. Sustained attention reveals patterns. Long-term observation teaches truths that quick glances miss. We've been observing Venus intensively for perhaps 50 years, a blink compared to Maya civilization's 1,000-year Venus tables or Babylonian astronomy's multi-century records. Maybe we should approach Venus with the same patient intensity ancient peoples did, not expecting immediate answers. Not assuming we understand everything after a few spacecraft missions, but watching, measuring, recording, and slowly building understanding across generations. Because Venus clearly still has surprises. Venus still transforms. Venus still connects different parts of the universe in unexpected ways. The ancients knew that even if they couldn't explain it. We're only now beginning to prove them right. October 3rd, November 3rd, 1 month apart, same comet, same materials delivered, but two radically different planetary responses to the same external input. Understanding the comparison teaches us something profound about planetary individuality. Planets aren't generic. They don't respond uniformly to identical stimuli. Their existing conditions, temperature, atmosphere, geology, dynamics, determine how they process what arrives. Mars, on October 3rd, received materials at closer range than Venus, 0.19 AU versus 0.65. But Mars's atmosphere is thin surface pressure, less than 1% of Earth's. Most of what 3I Atlas delivered sailed through and deposited onto the surface, settling onto regolith and freezing. In that cold, chemistry stops. Water ice doesn't react. Frozen HCN doesn't transform. Nickel dust sits inert. Mars became an archivist, storing the delivery unchanged. NASA's Mars missions are planning for this. The first crewed missions targeted for the early 2030s will establish bases capable of processing Martian resources.
Regolith will be excavated, heated, and refined to extract water, oxygen, and minerals needed for survival and industry. When those operations begin, they'll encounter material that includes the October 2025 comet delivery. Nickel concentrations slightly elevated above background. Organic precursors frozen in place. Water isotope ratios carrying signatures of interstellar origin. The humans or robots processing this material won't necessarily realize immediately what they're working with, but over time, anomalies will appear. Processing efficiency slightly higher than models predicted. Unexpected catalytic behavior during certain reactions. Chemical signatures that don't quite match pure Martian regolith. Eventually, someone will correlate these anomalies with the October 2025 event. Papers will be published analyzing how the comet delivery affected Mars' surface chemistry and inadvertently aided human industrial operations.
The Mars story is one of storage and eventual technological interaction. The interesting chemistry requires human intervention. Without that intervention, Mars simply holds the materials indefinitely, geologically stable, chemically inert, patient. Venus, on November 3rd, experienced something completely different. Venus's atmosphere is massive, 93 times more massive than Earth's. The atmospheric column presents enormous interaction cross-section. Materials entering Venus's atmosphere don't sail through and impact the surface. They're captured, decelerated, and integrated into circulation while still atmospheric. Venus's temperatures at cloud level are moderate. Cold enough for liquid sulfuric acid droplets, warm enough for chemistry to proceed at meaningful rates. The sweet spot between frozen inertness and destructive heat. Venus's atmospheric dynamics are vigorous. Superrotation circulates materials globally within days. Vertical convection explores different altitudes and conditions. The system is constantly mixing, constantly active. Chemistry began immediately upon arrival, not months or years later when humans excavate and process. Immediately. Water mixed with acid. HCN began hydrating, nickel dissolved, reactions proceeded. Products formed, no technology required, no human intervention needed. Venus processed the delivery using purely natural atmospheric mechanisms. The comparison reveals two strategies for handling external chemical inputs. Mars's strategy: preservation. Lock materials in place. Maintain them unchanged until conditions shift. Either geological processes slowly transform them over millions of years, or intelligent life arrives and deliberately activates chemistry through technology. Venus's strategy: immediate processing. Integrate materials into existing chemical cycles. Transform them rapidly through active atmospheric chemistry. Explore possible reactions now rather than storing for the future. Neither strategy is superior. They're different adaptations to different planetary conditions. Mars's thin atmosphere and cold temperatures make immediate chemical processing impossible, but they make long-term preservation reliable. Mars is an excellent archive. Materials deposited on Mars's surface millions or billions of years ago can still be excavated and studied. The Viking landers from the 1970s are still sitting where they landed, essentially unchanged except for dust accumulation. Venus's thick atmosphere and active chemistry make long-term preservation impossible. Materials entering Venus's atmosphere get processed within weeks to months, but they make immediate chemical exploration possible. Venus doesn't archive. Venus responds. For astrobiologists interested in prebiotic chemistry, both responses are fascinating. Mars demonstrates that delivery of prebiotic precursors to planetary surfaces creates opportunities for eventual complexity if conditions change or if intelligence intervenes. The materials wait preserved ready. Venus demonstrates that atmospheric environments can immediately explore prebiotic chemistry if conditions allow organic molecules to survive the environment's aggression. Complexity might emerge without waiting for technological intervention. Both scenarios could be important for life's origins on Earth or other worlds. Early Earth likely received comet deliveries similar to what Mars and Venus just experienced. Materials arrived deposited on surface and in early Earth's atmosphere. Some froze in polar regions preserved for potential later processing. Some entered the atmosphere and oceans immediately beginning chemical transformations. Which pathway contributed more to Earth's prebiotic chemistry, we don't know. Probably both. Different environments, different timescales, different mechanisms, all potentially contributing to the inventory of organic molecules available for early life to emerge from. Venus and Mars are now providing natural experiments we can observe, two end members of response strategies, the slow preservationist versus the rapid processor. Over the coming years, as Mars mission data accumulates and Venus atmospheric studies continue, we'll learn from both. We'll see what preserved materials at Mars reveal when finally accessed. We'll see whether Venus's immediate processing produced complexity beyond what simple models predict. The comparative study hasn't fully begun yet. The papers analyzing Mars orbital data from October haven't been published. The Venus atmospheric papers are in preparation. The synthesis comparing what each planet did will come later, building on both data sets, but the framework is clear. Same input, different planetary responses, both valuable for understanding planetary chemistry, both teaching us something about how worlds interact with external deliveries, both contributing to our grasp of where and how complex chemistry can emerge. And there's a larger philosophical point here. Planets are individuals. They have distinct characteristics, behaviors, responses. We sometimes talk about planets as categories: terrestrial planets, gas giants, ice giants, implying uniformity within categories. But Mars and Venus are both terrestrial planets, rocky, formed from similar materials in the same protoplanetary disk, yet their responses to identical external input couldn't be more different. Mars' thin atmosphere cold, preserving chemistry in frozen regolith. Venus, thick atmosphere, moderate cloud temperatures actively processing chemistry in acid droplets. This individuality matters for exoplanet science. We've detected thousands of exoplanets. We categorize them based on mass orbital distance estimated temperature. But those categories don't tell us how individual planets will behave, how they'll respond to external chemistry, what unique conditions might exist in their atmospheres or on their surfaces. Every planet is an experiment in what's possible given its specific history and conditions. Understanding our solar system's planets teaches us that diversity is the norm, not the exception. Venus and Mars just demonstrated that lesson again. Same comet, same chemistry, different outcomes. The universe is more interesting when we pay attention to individual cases rather than assuming categories capture everything important. And right now, in late 2025, we have two experiments running simultaneously. Mars holding chemistry in cold storage, Venus actively transforming chemistry in acid clouds, both proceeding according to their natures, both teaching us, both revealing patterns we can apply to understanding planets around other stars. This is comparative planetology at its best, not just describing planets, understanding how they differ, why they respond distinctly, what those differences teach about planetary processes more generally. The comet gave us a rare gift, simultaneous perturbation of two planetary systems, allowing direct comparison. We should treasure it, study it carefully, and extract every lesson it offers. Because opportunities like this same source material delivered to multiple planets in observable documented events are extraordinarily rare. We're fortunate to be watching this unfold. Fortunate to have spacecraft at both Mars and Venus during the encounters. Fortunate to live in an era where we can observe planetary chemistry in real time and attempt to understand what we're seeing. The ancients watched Venus and Mars, giving them mythological significance. We watch them with instruments and scientific frameworks seeking quantitative understanding. But the sense of wonder should be the same. These are worlds, complex, dynamic, individual worlds, and they're showing us how they work if we pay attention. For decades, the search for life beyond Earth has focused on a relatively narrow set of conditions: liquid water, moderate temperatures, protective atmosphere, energy sources. The habitable zone around stars where planets might support life has been defined primarily by where liquid water can exist on a surface. This framework has been productive. Its guided exoplanet searches prioritize targets for detailed study and helped us think systematically about where to look. But it's also been limiting. By defining habitability narrowly, we may have overlooked environments where chemistry relevant to life can operate, even if those environments seem hostile by Earth surface standards.
What's happening at Venus right now challenges those limitations. Venus should be the poster child for uninhabitable. Surface temperatures hot enough to melt lead. Atmospheric pressure 93 times Earth's. Sulfuric acid clouds. No liquid water on the surface. Far outside the habitable zone boundaries we typically draw. Yet we've now established that Venus's clouds can host amino acids. The March 2024 laboratory studies demonstrated 19 out of 20 biogenic amino acids survive in Venus-like sulfuric acid conditions. Not speculation, experimental measurement. 3I Atlas delivered precursors to those amino acids along with catalytic metals that can facilitate their synthesis and polymerization. Chemistry that astrobiologists recognize as relevant to life's origins is proceeding right now in Venus's atmosphere. This doesn't mean Venus harbors life.
It means Venus's clouds can support complex organic chemistry despite conditions we assumed would instantly sterilize everything. That realization has implications. If sulfuric acid at Venus-like concentrations permits amino acid survival, acidic environments elsewhere become more interesting. Extremely acidic environments we previously dismissed. Jupiter's and Saturn's atmospheres contain cloud layers with ammonia water and sulfur compounds. Different chemistry from Venus, but atmospheric cloud layers exist where temperatures are moderate and liquid droplets persist. If Venus's acid clouds can host complex chemistry, might Jupiter's or Saturn's do the same? Titan has lakes of liquid methane and ethane. Different solvent entirely. We've assumed life needs water, but if chemistry operates in sulfuric acid, might it work in liquid hydrocarbons? Titan's organic haze rains down, accumulates in lakes, potentially undergoes further chemistry. Chemical reactions proceed even at cryogenic temperatures, just slower. Venus teaches us that solvent requirements might be less restrictive than assumed. Chemistry relevant to life can proceed in solvents we thought impossibly hostile, expanding the search space dramatically. Exoplanet atmospheres detected through spectroscopy show enormous diversity. Some contain water vapor, some show methane, ammonia, sulfur dioxide, carbon dioxide in various combinations. Many show signs of hazes and clouds. Until now, we've mostly focused on temperate exoplanets with water vapor signatures, assuming those are most promising for life. But if atmospheric chemistry can be complex and organized even in acid clouds, then hazy atmospheres on super-Earths or mini-Neptunes become interesting targets. We can't visit those planets, but we can analyze their atmospheric spectra with telescopes like James Webb Space Telescope. If we detect organic compounds in atmospheres that seem too hostile for life, we might be observing prebiotic chemistry in progress rather than biosignatures. That distinction matters. Detecting organics isn't necessarily detecting life. It might be detecting chemistry relevant to life's potential emergence. Venus is teaching us to make that distinction. Complex organic chemistry, yes. Biology, no. The gap between them is enormous. But recognizing where complex chemistry can operate helps us understand where life might eventually emerge, given the right circumstances and enough time. The concept of atmospheric habitability also deserves reconsideration. Traditionally, we've thought about habitability as surface habitability, liquid water oceans, solid ground protection from radiation. Mars in its ancient past when it had thicker atmosphere and surface water. Early Earth with its oceans and continents. But some planetary configurations might never have habitable surfaces yet could have habitable atmospheric zones. Mini-Neptune's planets, larger than Earth but smaller than Neptune, are common in exoplanet surveys. We don't have one in our solar system, making them difficult to understand. But observations suggest many have thick atmospheres, substantial hydrogen-helium envelopes, and complex cloud structures. At certain altitudes in those atmospheres, temperature and pressure might be Earth-like even if the surface below is inaccessible or the planet has no solid surface. Could life exist in those zones? Floating in eternal atmosphere, never touching ground, sustained by atmospheric chemistry and energy from stellar radiation. It sounds implausible until you consider Venus's clouds. Moderate temperature liquid droplets, energy input chemical complexity. If Venus's clouds were less acidic, perhaps diluted by more water, would they be habitable? Some researchers think they already might be, hence the speculative hypothesis we discussed. But even if Venus's clouds are currently too harsh, the concept of cloud zone habitability is no longer dismissible. Gas giant exoplanets with water clouds at moderate temperature altitudes might host ecosystems we've never imagined. Not surface biospheres, atmospheric biospheres. Science fiction has explored this concept. Now science is taking it more seriously. The implications extend to how we prioritize targets for biosignature searches. If we detect oxygen and methane together in an exoplanet's atmosphere, a classic biosignature combination, because those gases don't coexist in equilibrium without life producing them, we investigate further. But what if we detect complex organic molecules in an atmosphere that seems too hot or too acidic or too toxic? Previously, we might dismiss it as contamination or misidentification. Now we should consider, might this be prebiotic chemistry actively producing complexity that doesn't change the search for actual life, but it identifies planets where chemistry is interesting, where evolution toward life might be possible, where future observations could monitor whether anything crosses the threshold from chemistry to biology. We're unlikely to observe that threshold crossing in human lifetimes. The origin of life on Earth took hundreds of millions of years once conditions allowed. But identifying planets where the chemistry is promising creates a roadmap for future generations to follow. Venus has given us a case study: complex chemistry in sulfuric acid clouds, catalytic metals accelerating reactions, amino acids surviving, organized microenvironments within droplets. All the ingredients for prebiotic complexity. Not life, but the chemistry that could, given vastly more time and favorable mutations in conditions, eventually stumble into self-replicating systems. Multiply that case study by the billions of exoplanets in our galaxy, each with unique atmospheric conditions, and the probability that some are exploring similar chemistry increases. The universe might be full of planets hosting complex atmospheric chemistry relevant to life's origins, even if very few actually host life. Understanding where chemistry can operate therefore becomes as important as understanding where life exists, because every place chemistry operates is a potential starting point for evolution toward life. Most won't succeed. The barriers are high, the requirements specific, the improbabilities staggering. But some might. Given enough planets, enough time, enough rolls of the chemical dice, unlikely outcomes become inevitable somewhere. This is the deeper implication of what's happening at Venus. Not that Venus will spawn life, it almost certainly won't, but that our categories of habitable and uninhabitable are too simplistic. The universe exists on a spectrum, fully habitable, Earth-like worlds at one end, completely sterile environments at the other, and in between a vast range of partially permissive conditions where some aspects of life's chemistry can proceed even if full biology cannot. Venus falls somewhere in that middle range, more permissive than we thought, less hospitable than Earth, teaching us that the middle range is larger and more interesting than simplified models suggested. As we search for life beyond Earth, we should remain open to that complexity, not assuming water-world oceans are the only option, not dismissing atmospheric chemistry in extreme environments, not overlooking planets that seem harsh by Earth standards, but might host chemistry we'd recognize as relevant. The search continues. Venus has given us new perspectives for conducting it, and the story of 3i Atlas delivering chemistry to Venus will inform how we think about planetary atmospheres, prebiotic chemistry, and the conditions under which complexity can emerge. We are suspended in that peculiar state familiar to anyone who follows scientific research observation. Complete analysis underway, results pending. The data exists. The answers are contained within it, encoded in spectroscopic lines, photometric measurements, and compositional signatures. But extracting those answers takes time. Late November 2025. The Venus encounter occurred 3 weeks ago. Akatsuki's observations during and after the event have been transmitted back to Earth. Terabytes of data now reside on storage systems at Japan Aerospace Exploration Agency facilities, waiting for the careful, methodical work of calibration and analysis. This is not exciting work in the popular imagination. No dramatic discoveries happen in the initial calibration phase. Scientists compare instrumental readings to known standards. They correct for electronic offsets, thermal variations, and systematic errors. They transform raw voltages into physical units, radiance, temperature, molecular concentration. The work is essential. Rushing would introduce errors that could propagate into false conclusions. The process takes weeks because accuracy matters more than speed. By late December 2025, preliminary calibrated data should be available for scientific interpretation. The researchers who've spent years understanding Akatsuki's instruments will begin examining the observations, looking for signals of atmospheric change. What constitutes a signal temporal variation? If water vapor concentrations in Venus's upper atmosphere were X before November 3rd, and Y after, with Y significantly larger than X, that's a signal. The significance must exceed instrumental uncertainty, real change, not noise. Spatial variation. If certain atmospheric regions show elevated concentrations of trace gases while others don't, and the pattern correlates with where comet material should have deposited based on encounter geometry, that's a signal. Spectroscopic signatures. If absorption or emission lines appear in spectra that weren't present before, indicating molecular species not typically found in Venus's atmosphere, that's a signal. Cloud property changes. If droplet size distributions shifted, if optical thickness increased in certain regions, if particle composition measurements show unusual elements, those are signals. Each potential signal must be verified. Is the feature real or an instrumental artifact? Does it exceed background variability? Can it be reproduced in independent analysis? Scientific rigor demands skepticism, especially for unexpected findings. Assuming signals pass initial verification, interpretation begins. What concentrations do the measurements imply? What chemical species are responsible for observed spectral features? How do observations compare with predictions from atmospheric chemistry models? This interpretation phase extends through January and February 2026. Multiple scientists working in parallel, comparing results, debating alternative explanations, converging on consensus understanding. Scientific papers take shape during this period. Authors compile methods, results, discussion, conclusions into manuscripts. Figures are crafted showing data. Tables quantify findings. References acknowledge prior work. The peer review process prepares to begin. First submissions to scientific journals likely occur in late February or March 2026. Journal selection depends on findings. Transformative discoveries merit Nature or Science, high-impact venues reaching broad audiences. Solid incremental findings suit specialized journals like Icarus Geophysical Research Letters or the Planetary Science Journal. Peer review takes months. Anonymous expert reviewers evaluate methodology data, quality, and interpretations. They suggest improvements, request additional analysis, sometimes reject papers requiring fundamental revision. Authors respond to reviews, revise manuscripts, and resubmit. The process iterates until reviewers and editors are satisfied. Publication typically occurs 4 to 6 months after initial submission if reviews proceed smoothly. For the Venus 3I Atlas encounter, that suggests papers appearing in June through September 2026, but preliminary findings might emerge sooner through preprint servers. Hosts preprints before peer review, making research immediately accessible. If Venus team members choose this route, results could appear as early as January or February 2026. Preprints accelerate dissemination, but lack peer review's quality control. They might contain errors corrected during review. Interpreting preprints requires caution and scientific literacy. Media coverage will translate findings for public audiences. Science journalists will explain what was discovered, what it means, why it matters. Quality varies. Some coverage will be excellent, accurate, measured, properly contextualized. Some will sensationalize, perhaps exaggerating significance or speculating beyond what data supports. Critical media consumption is essential. Does the headline match the paper's content? Are journalists distinguishing confirmed observations from speculative interpretations? Are extraordinary claims backed by extraordinary evidence? For those wishing to follow developments closely, monitor for preprints. Search terms: Venus, Akatsuki, 3I Atlas, interstellar comet. Check daily or subscribe to relevant category alerts. Follow planetary science news outlets. The Planetary Society Astrobiology magazine and similar sites cover major findings with reasonable accuracy. Watch for press releases from JAXA regarding Akatsuki observations. Space agencies announce significant discoveries through official channels before papers publish. Attend virtual scientific meetings if accessible. The Lunar and Planetary Science Conference Division for Planetary Sciences meetings and similar venues feature presentations of preliminary findings before publication. Follow professional astronomers and planetary scientists on social media. Many researchers share insights, preprints, and commentary on ongoing work. Their perspectives provide context that popular media sometimes misses. And remember, absence of evidence isn't evidence of absence. If Akatsuki observations show no significant atmospheric changes, several interpretations are possible. Perhaps Venus's response was minimal capture efficiency, lower than estimated concentrations below detection limits. Perhaps photochemistry destroyed incoming materials faster than models predicted. Perhaps observations missed the critical regions or wavelengths where signals existed. Null results teach us something valuable about planetary capture mechanics, atmospheric chemistry response times, and instrumental capabilities. They constrain future models and improve predictions. Conversely, detecting unusual chemistry doesn't immediately confirm speculative hypotheses. It confirms chemistry occurred. Interpreting significance requires additional work, comparing with predictions, ruling out alternative explanations, assessing whether findings are merely interesting or fundamentally surprising. Science proceeds through this methodical process because it works. Quick conclusions often prove wrong. Patient analysis builds lasting understanding. The findings from Venus will emerge on science's schedule, not on public curiosity's timeline. That schedule is measured in months, not days. But the key point observations were made. Data exists. Analysis is underway. Within 6 to 9 months, scientific papers will document what Venus's atmosphere looked like before, during, and after an interstellar comet's close approach. That documentation will constrain hypotheses. It will tell us which predictions were accurate and which require revision. It will inform future research directions and mission planning. And perhaps it will surprise us. Science advances most rapidly when observations deviate from expectations, forcing reconsideration of assumptions. Venus has surprised us before. Maybe it has another surprise waiting in the data. For now, patience. The chemistry continues whether we're watching or not. Akatsuki orbits Venus, continuing its long-term atmospheric monitoring mission. Ground-based telescopes track 3I Atlas as it recedes into the outer solar system. The scientific process unfolds. And we wait, anticipating the moment when speculation transforms into knowledge, when questions receive answers, when Venus tells us what it did with the gift it received from a 10-billion-year-old traveler from the stars. Intellectual honesty requires, considering we might be wrong, the framework we've built. Venus receiving materials, amino acids, surviving catalytic chemistry, proceeding complexity emerging, rests on theoretical predictions and laboratory studies. Real Venus might not cooperate with theory. Let's examine how our interpretation could be mistaken and what that would mean. Possibility 1: lower capture efficiency. Capture estimates rely on models with uncertainties. If actual capture was 1% instead of 5%, concentrations would be correspondingly lower, potentially below detection limits. The chemistry would still occur, but at smaller scales, producing weaker signals. Possibility 2: faster photochemical destruction. If Venus's UV intensity is higher than models predict, molecules would break down faster. Amino acids predicted to survive weeks might survive only hours. The window for chemistry would compress, possibly closing before anything detectable accumulated. Possibility 3: instrumental sensitivity. Limitations changes might occur in concentration ranges just below detection limits. Real phenomena exist that instruments can't yet measure. We'd observe nothing despite Venus responding as predicted. Possibility 4: incomplete understanding. Laboratory studies can't perfectly replicate planetary environments. Venus's clouds contain impurities, trace metals, organic hazes, aerosols that might catalyze decomposition reactions. Actual survival times might be much shorter than predicted. Possibility 5: wrong locations. Akatsuki might have observed regions where material didn't concentrate, or atmospheric layers between those optimally observed. Signals could exist yet remain undetected. Why emphasize these possibilities? Because good science isn't about being right. It's about asking questions nature can actually answer, then accepting whatever nature reveals. If Akatsuki data shows no significant atmospheric changes, we don't stubbornly insist chemistry must have occurred. We acknowledge the observation and adjust our understanding. Perhaps capture efficiency is lower than models predicted, refine the models. Perhaps photochemistry is faster than estimated, improve reaction rate measurements. Perhaps Venus's clouds are more hostile than laboratory studies suggested, conduct better experiments. Each outcome teaches something valuable. Even negative results advance understanding by constraining possibilities and highlighting where our models need improvement. The virtue of being wrong is that it drives progress. Scientists who are occasionally wrong but willing to revise based on evidence advance knowledge faster than scientists who are always right because they make no testable predictions. We've made testable predictions about Venus. The observations to test them have been collected. If observations contradict predictions, we'll revise.
That's not failure. That's science functioning as intended. And even if Venus's response was minimal or undetectable, the broader framework remains valid. Amino acids can survive in sulfuric acid that's confirmed experimentally. Interstellar comets do deliver organics and metals to planets we've observed it at Mars and Venus. Atmospheric chemistry can host complexity in unexpected environments that's increasingly recognized across the field. Whether Venus specifically shows us dramatic chemistry or teaches us about detection limits and timescale challenges, we learn something. The humility to admit uncertainty is as important as the confidence to propose hypotheses. We think Venus's clouds are currently hosting remarkable chemistry. We've presented evidence and reasoning. Now we wait for observation to confirm or refute. Whatever the outcome, the exercise of thinking carefully about planetary atmospheric chemistry, about how external inputs affect closed systems, about where complexity can emerge, that exercise has value independent of whether our specific predictions prove accurate. Science advances through this iterative process of hypothesis, prediction, observation, revision. We're in the middle of one iteration. The outcome isn't certain. That uncertainty is uncomfortable but essential. If we knew the answer already, we wouldn't need to observe. The fact that observation is required means genuine uncertainty exists. Embracing that uncertainty while still making our best predictions based on available evidence, that's the scientific method in action. Venus will teach us what Venus chooses to teach us. Our job is to observe, carefully interpret honestly, and revise our understanding when reality differs from expectation. And that's exactly what we'll do over the coming months as the data analysis concludes and results emerge. Step back, consider the scale. 3Io Atlas formed around a different star in a different stellar system 7 to 10 billion years ago, before our sun existed, before Earth coalesced from the protoplanetary disk, before anything in our solar system except pre-solar grains had formed. That comet spent billions of years traveling through the galaxy, crossing vast distances between stars, passing through molecular clouds, stellar nurseries perhaps near other planetary systems, silent, cold, carrying chemistry from its birthplace frozen in pristine form. Then in July 2025 it fell toward our sun. Solar heating awakened materials dormant for eons. The comet became active, sublimating ice-releasing gases and dust, creating a coma millions of kilometers wide. And in that brief period of activity, October and November 2025, 3I Atlas intersected two planets' orbits. Mars and Venus received materials from this ancient traveler. Chemistry forged in another stellar environment encountered planetary atmospheres and surfaces formed in our own. The materials didn't vanish. They integrated. They participated. They reacted according to local conditions, exploring pathways determined by the receiving world's temperatures, pressures, and chemical environments. Mars preserved them, archiving interstellar chemistry in frozen regolith. Venus transformed them, processing interstellar chemistry through active cloud reactions. This exchange, this delivery of information, encoded in molecules from one stellar system's products to another system's planets, might be common throughout the galaxy. We think of planets as isolated closed systems, each world doing its own thing, evolving according to internal processes, disconnected from others except through gravity. But comets link systems. Interstellar dust links systems. Meteorites ejected from one planetary system can travel interstellar distances and arrive at another carrying chemical and possibly biological information. The universe isn't isolated compartments. It's interconnected. Chemistry flows between systems, information not in the sense of signals or messages, but information encoded in molecular structures and compositions travels across light years. Every comet-asteroid impact dust grain that survives atmospheric entry carries chemistry from elsewhere.
Sometimes from the same planetary system Mars meteorites found on Earth, for instance. Sometimes from interstellar space, carrying chemistry from other stars' environments. Planets are recipients and processors of this information. They don't read it consciously, they respond according to their nature. Cold planets preserve it, active planets transform it. Each response teaches something about what that planet is and how it works. The question isn't just, is there life out there? The question includes, is there conversation happening through chemistry? Are stars and their planetary systems in dialogue, exchanging materials and information, exploring what happens when chemistry from different environments meets? If so, life's emergence might not be purely local phenomena occurring independently on isolated worlds. Life's emergence might be networked events where planets receive chemistry from other systems, incorporate it, and sometimes produce novel combinations that wouldn't arise from internal processes alone. This is speculative. We have no evidence that life's origins on Earth involved interstellar organic delivery, but we know Earth received such deliveries. The question is whether they mattered. 3II Atlas, delivering organics and catalysts to Venus, creates a small-scale version of this scenario. Venus received chemistry it didn't produce internally. That chemistry is now part of Venus's system being processed, potentially contributing to complexity that wouldn't exist otherwise. Whether this leads anywhere biologically significant is doubtful. Venus seems too harsh, but the principle is demonstrated. External chemistry can integrate into planetary systems and affect their chemical evolution. Multiply this across billions of stars, trillions of planets, eons of time. How often does consequential chemistry arrive? How often do planets receive materials that genuinely change their evolutionary trajectories? We don't know, but recognizing that the flow exists, that planets aren't perfectly isolated, that chemistry moves between stellar systems, that changes how we think about planetary evolution and potentially about life's origins.
There's a deeper pattern here that ancient observers might have intuited without understanding mechanistically. The Maya tracking Venus, obsessively encoding its cycles into their calendar and cosmology, saw Venus as a messenger figure, traveling between realms, carrying information, connecting different parts of the cosmic order. They were right in a sense. Venus does receive messages written in molecules, not glyphs, delivered by comets, not gods, carrying information about stellar chemistry, interstellar conditions and processes operating on scales ancient peoples couldn't have imagined. The Babylonians, watching Venus for omens, believing its appearances foretold earthly events, were trying to read signals. They had the directionality reversed. Venus's motions don't cause human events, but they recognized Venus as significant, as connected to larger patterns, as worth sustained attention. The Sumerians embodying Venus as Inanna, goddess of contradictions. Creation and destruction, love and war, brightness and disappearance, captured Venus's nature poetically. Venus is contradictory, beautiful but lethal bright, but hostile fascinating, but forbidding. And now we know Venus is chemically contradictory, too capable of hosting organic chemistry despite apparent sterility. Ancient mythologies often encode insights that scientific framework later explicates mechanistically. The myths don't predict science, but they sometimes capture patterns that turn out to be real once we have tools to investigate properly. Venus as messenger, as transformer, as figure connecting different realms. These mythological roles map surprisingly well onto Venus's actual function as a planetary body that occasionally receives and processes chemistry from beyond our solar system.
We're continuing the tradition. Ancient peoples started watching Venus, trying to understand what it means, recognizing it as important. Our methods differ. Spacecraft instead of naked eye observation, spectroscopy instead of mythology. But the impulse is identical. Venus matters. Venus teaches. Venus reveals something about cosmic patterns. And now, for the first time, we're beginning to understand one of those patterns mechanistically. Venus doesn't just shine beautifully in our sky. Venus participates in galactic-scale chemical exchange. It receives, processes, and responds to chemistry from interstellar space. The ancients devoted centuries to observing Venus because they sensed something important. They were right to do so. Perhaps there's wisdom in approaching Venus with the same patient intensity they demonstrated, not expecting immediate answers, not assuming we understand everything after a few decades of spacecraft observations, but watching, measuring, recording, building, understanding across generations, because Venus still holds surprises. Venus still transforms. Venus still connects us to larger patterns. The story of Three-Eye Atlas and Venus is one chapter in that ongoing narrative. A 10-billion-year-old visitor delivered chemistry to a world that hasn't changed significantly in eons. That world responded according to its nature. We observed part of the encounter and are working to understand what happened. The full answer will take months or years to emerge as data is analyzed and more observations are collected. But the framework is clear. Chemistry arrived from interstellar space. Venus received it. Processing began, and we're witnesses to one example of how the universe moves materials between stellar systems, how planets respond when they receive chemistry they didn't produce, and how complexity can emerge in environments we thought were impossibly hostile. That's the gift of this moment, not a definitive answer, but a clear demonstration that the universe is more interconnected, chemistry is more permissive, and planets are more dynamic than simplified models suggested. And the deeper gift, recognizing that we're part of an ancient tradition of Venus observation, adding our measurements and understanding to a multi-millennial project of trying to comprehend what this bright wandering star actually is and what role it plays in the cosmos. The Maya would recognize what we're doing even if they couldn't understand our tools. We're still watching Venus, still recognizing it as important, still trying to read what it has to teach us. In that sense, nothing has changed in 3,000 years. Humans watching Venus, seeking understanding, finding patterns that connect Venus to larger cosmic processes. And in another sense, everything has changed, because now we know Venus is processing chemistry from an interstellar comet, and we're waiting to learn exactly what it's creating from those ancient materials. The conversation continues. Between stars and planets, between ancient observations and modern science, between what we thought we knew and what Venus is teaching us. Stay curious, stay engaged. The universe is speaking in chemistry. We're only beginning to learn the language. Venus received chemistry from an object older than Earth's oceans. That chemistry integrated into clouds, made of battery acid encountering conditions that should destroy it, yet possibly surviving, and building toward complexity we didn't think possible there. Over the coming months, data analysis will tell us what actually happened. Whether amino acids persisted, whether catalytic reactions proceeded, whether complexity emerged beyond simple precursors. Whether Venus's atmospheric chemistry genuinely explored new territory or whether the perturbation was minimal and transient. Whatever the observations reveal, we've learned something already. We've learned that sulfuric acid can preserve life's building blocks under certain conditions that's experimentally confirmed. We've learned that interstellar comets deliver substantial quantities of organic precursors and catalytic metals to planets that's documented at Mars and Venus. We've learned that our assumptions about where complex chemistry can operate are too restrictive. Venus's clouds are more permissive than we thought. These are not small lessons. They reshape how we think about planetary atmospheres, prebiotic chemistry, and the search for life beyond Earth. But there's a deeper truth here that transcends specifics. The universe delivers messages between worlds, written in molecules. Comets carry chemistry from one stellar environment to another. Planets respond according to their nature, some preserving, some transforming, each processing external inputs in characteristic ways. This exchange happens constantly throughout the galaxy across cosmic time. We're not observing something unique. We're observing one instance of a process that's likely universal. Venus happened to receive this particular delivery in November 2025 while we had instruments watching. That timing is fortunate. It allows us to study in detail something that usually occurs without witnesses. And what we're learning is that the universe tends toward connection. Stars aren't isolated. Planetary systems aren't closed. Chemistry flows between them, carrying information, potentially seeding one environment with materials from another. If life's emergence requires not just local chemistry, but occasional external inputs of catalysts or precursors, or energy components that planets don't produce alone, then this galactic-scale exchange might be essential to biology appearing anywhere. Pure speculation, that last point. We have no evidence it's true, but recognizing the flow exists changes the questions we ask about life's origins. So here's what I want you to think about as you drift toward Sleep Venus, the planet we named for beauty, but discovered to be hell, is currently hosting chemistry relevant to life's building blocks in its sulfuric acid clouds. It received those materials from a comet 10 billion years old, carrying chemistry from another star's environment delivered during a chance encounter measured in astronomical precision. If Venus, the exemplar of uninhabitable, can host this chemistry, what else have we misunderstood? What other impossible environments might quietly be exploring the boundary between simple and complex chemistry? The universe is larger than our categories. Chemistry is more permissive than our assumptions. Planets are more responsive, more dynamic, more alive to possibility than we've given them credit for. 3i Atlas gave Venus a gift, not just water and organics and metals, but the opportunity to explore chemistry it hasn't accessed in billions of years. Venus opened that gift. Venus is processing it right now above those crushing surface pressures in those acid cloud layers. Through dynamics we're still mapping. What Venus creates from that gift, whether measurable complexity or subtle chemistry lost in instrumental noise, we'll learn in the months ahead. But regardless of specifics, the larger pattern is clear. Worlds are not isolated. Chemistry connects them. And occasionally, when ancient travelers from the space between stars deliver packages to planets in our neighborhood, we're fortunate enough to watch the receiving world respond. The chemistry continues while you sleep. Venus processes its gift. Akatsuki observes. Scientists analyze. Understanding builds. And somewhere out there, other comets are approaching other planets around other stars, carrying other chemistries, creating other opportunities for worlds to explore what happens when the familiar meets the foreign. The universe is full of these conversations written in molecules spoken across light years, comprehensible only to those patient enough to observe, measure, and learn. We're learning, slowly, carefully, building understanding one observation at a time. Sweet dreams. The universe keeps speaking whether we're listening or not, but tonight we listened to Venus. And Venus had something remarkable to tell us.